Hello there, and welcome. Tonight I want to take you somewhere quiet, somewhere deep, somewhere that exists all around you right now but remains invisible to your eyes. I want to take you to the edge of reality itself, to a place where the solid walls you know become something else entirely, something softer, something that whispers of possibilities you might never have imagined. Tonight we're going to explore one of the most beautifully strange phenomena in all of physics, a mystery that unfolds constantly in the atoms of your body, in the heart of distant stars, and in the quiet electronic devices that surround you as you rest. We're going to explore why particles can tunnel through walls they don't have enough energy to cross, and in doing so, we're going to discover something profound about the nature of reality itself. As you settle in, wherever you are right now, I wonder what time it is where you're listening. Perhaps it's late at night, and the world outside has grown quiet. Perhaps it's early morning, and you're seeking a gentle way to drift back to sleep. Or maybe it's somewhere in between, in one of those soft, timeless moments when the boundary between waking and sleeping becomes beautifully blurred. Wherever you are, whatever time zone cradles you right now, you're part of a vast, interconnected world of listeners, all of us drawn together by curiosity about the mysteries that surround us. And if you find yourself enjoying this gentle journey through the quantum realm, if these soft explorations of physics help you rest and wonder at the same time, perhaps you might like to subscribe or follow along for more of these sleepy adventures into science. Think of it as joining a quiet community of nighttime wanderers, all of us exploring the universe's secrets together, one peaceful documentary at a time. But for now, just rest, just listen, just let yourself drift as we begin our journey into the quantum world. Imagine, if you will, a simple wall. Not a quantum wall yet, just an ordinary wall like the ones that surround you right now. Perhaps it's made of brick, or wood, or plaster. It stands there, solid and dependable, separating one space from another. If you were to throw a ball at this wall, you know exactly what would happen. The ball would bounce back. It doesn't have enough energy to pass through the wall, so it returns to you, following the predictable laws of classical physics that govern our everyday world. This is the physics of our intuition, the physics that kept our ancestors safe, that told them where they could go and where they couldn't, what was possible and what was not. Now imagine a different kind of wall, not one made of bricks or wood, but one made of energy itself. Picture a hill, a smooth, rounded hill that rises up before you. If you're riding a bicycle and you approach this hill, you need a certain amount of energy to reach the top. If you're going too slowly, if you don't have enough energy, you'll roll partway up and then roll back down. You cannot reach the other side. This too follows our intuition. Energy is needed to overcome barriers, whether they're physical walls or energetic hills. This is the world as we know it, the world as it appears to be, solid and predictable and bound by rules that make perfect sense. But tonight, we're going to discover that at the smallest scales of reality, these rules begin to soften, to blur, to become something altogether more mysterious. Down at the level of individual particles, down where electrons dance around atomic nuclei, where protons and neutrons huddle together in the hearts of atoms, the walls and barriers we thought we understood transform into something else entirely. They become not solid obstacles, but something more like suggestions. They become barriers that can be crossed even when there isn't enough energy to climb over them, walls that can be passed through as if by magic, except it isn't magic at all. It's quantum mechanics, and it's happening everywhere, all the time, right now, in the atoms that make up your body, in the air you're breathing, in the stars that shine in the darkness above. The phenomenon we're exploring tonight is called quantum tunneling, though that name hardly does justice to its strange beauty. When physicists first discovered it in the early 20th century, they could barely believe what their equations were telling them. Here was nature, supposedly bound by rigid laws, suddenly revealing that particles could do something that seemed impossible. They could appear on the other side of barriers they didn't have enough energy to cross. It was as if a ball thrown at a brick wall could sometimes somehow appear on the other side without breaking through, without going over, without going around. It simply appeared there, as if the wall had momentarily become transparent to its passage. To understand how this is possible, we need to let go of our image of particles as tiny, solid spheres, like miniature marbles rolling through space. This picture, comfortable as it might be, is not how nature actually works at the quantum scale. Instead, Particles are something far more ethereal, far more mysterious. They are, in a sense, clouds of possibility, waves of potential existence that spread out through space. A particle doesn't exist at a single, definite point until we measure it. Before that measurement, it exists as a kind of probability cloud, a mathematical entity called a wave function that describes where the particle might be found if we look for it. This wave-like nature of particles is not just a theoretical construct, not just a convenient mathematical fiction. It's a fundamental aspect of reality that has been confirmed by countless experiments over the past century. When we send electrons through thin slits, they create interference patterns like waves do. When we cool atoms down to near absolute zero, we can see them behaving as waves, spreading out and overlapping in ways that solid particles never could. This wave nature is always there, always present, though it becomes less noticeable as objects get larger and heavier. By the time we reach the scale of everyday objects, the wave nature has become so negligible that we can ignore it entirely. But at the quantum scale, it dominates everything. Now, when one of these particle waves encounters a barrier, something remarkable happens. Unlike a classical particle that would simply bounce back, the quantum wave doesn't stop abruptly at the barrier's edge. Instead, it penetrates into the barrier, though it weakens as it goes deeper. It's like a sound wave entering a thick wall. The sound doesn't stop instantly at the wall's surface but penetrates a little way in, growing fainter with distance. For quantum particles, this penetration is described by what physicists call exponential decay. The wave function doesn't drop to zero immediately at the barrier. Instead, it fades away exponentially, which means it decreases rapidly but never quite reaches zero. If the barrier is thin enough, something extraordinary can happen. The wave function, though weakened, can extend all the way through the barrier and emerge on the other side. It's faint there, much fainter than it was before the barrier, but it's not zero. And in quantum mechanics, anywhere the wave function is not zero, there's a probability, however small, of finding the particle there. This means that sometimes, when we measure where the particle is, we'll find it on the far side of the barrier, even though it never had enough energy to climb over it. The particle has tunneled through. This might sound like some exotic phenomenon that only happens in specialized physics laboratories, but nothing could be further from the truth. Quantum tunneling is happening constantly, everywhere in the universe. It's happening in the sun right now, where protons are tunneling through the electromagnetic barriers that keep them apart, allowing them to fuse and release the energy that lights our days and warms our planet. Without quantum tunneling, the sun would not shine, at least not in the steady, life-giving way it does. The temperature at the sun's core, though incredibly hot by our standards, is actually not hot enough for protons to have sufficient energy to overcome their mutual electromagnetic repulsion through classical means. They need tunneling to get close enough to fuse, and tunnel they do, billions upon billions of times each second. Quantum tunneling is happening in your body right now, in the complex biochemical reactions that keep you alive. Enzymes, those remarkable molecular machines that catalyze the chemical reactions of life, often rely on tunneling to move protons or electrons from one place to another. Without tunneling, many of these reactions would proceed so slowly that life as we know it would be impossible. The very chemistry of life depends on particles being able to cross barriers they classically shouldn't be able to cross. It's happening in the electronic devices around you, in the computer chips and memory devices that store and process information. Many modern electronic components deliberately exploit quantum tunneling. Flash memory, the kind used in USB drives and solid-state drives, stores information by forcing electrons to tunnel through an insulating barrier. The scanning tunneling microscope, one of our most powerful tools for imaging individual atoms, works by measuring the tiny current of electrons that tunnel between a sharp metal tip and a surface. These technologies would be impossible without quantum tunneling. As you lie there, breathing slowly, consider that with each breath, countless particles in your lungs are exploring the boundaries of their quantum walls. Most bounce back, following classical paths, but some, a precious few, tunnel through barriers they have no classical right to cross. These quantum events are not disrupting your biology, they're an integral part of it. Evolution has had billions of years to incorporate quantum effects into the machinery of life, and it has done so with remarkable subtlety and sophistication. The discovery of quantum tunneling emerged from one of physics' great puzzles in the early 20th century. Scientists had noticed that certain radioactive elements emitted alpha particles, which are essentially helium nuclei, 2 protons and 2 neutrons bound together. What puzzled them was how these alpha particles could escape from the nucleus at all. The nuclear force that holds the nucleus together creates a barrier around it, like a wall surrounding a fortress. Calculations showed that the alpha particles inside didn't have nearly enough energy to climb over this wall, yet somehow they were escaping. It was as if prisoners were escaping from a prison without climbing the walls, without digging tunnels, without breaking through the gates. They were simply appearing outside. In 1928, a young physicist named George Gamow, applying the newly developed mathematics of quantum mechanics, proposed a radical solution. The alpha particles were tunneling through the nuclear barrier. Even though they didn't have enough energy to go over it, their wave nature allowed them a small probability of appearing on the other side. The probability was tiny for any individual particle, but with the enormous number of particles in even a small sample of radioactive material, tunneling events would happen regularly enough to account for the observed radioactive decay. This explanation was revolutionary. It was one of the first major successes of quantum mechanics in explaining a phenomenon that classical physics couldn't handle. It showed that quantum mechanics wasn't just an abstract, mathematical theory, but a description of real physical processes happening in nature. The success of tunneling theory in explaining radioactive decay opened physicists' eyes to the possibility that tunneling might be important in many other contexts as well. As we drift deeper into this quantum realm, notice how different it is from the solid, predictable world of our everyday experience. In the classical world, boundaries are absolute. A wall is a wall, a barrier is a barrier. You're either on one side or the other, and moving from one side to the other requires a definite expenditure of energy. But in the quantum world, boundaries become fuzzy, probabilistic. A particle can be partially on both sides of a barrier at once, existing in a superposition of states until a measurement forces it to choose. The barrier itself is less like a solid wall, and more like a region where the particle's existence becomes less probable, but never impossible. This fuzzy, probabilistic nature of quantum reality might seem unsettling at first, as if the solid ground of reality has turned to mist beneath our feet. But there's something deeply beautiful about it too. It means that nature, at its most fundamental level, is not rigid and mechanical, but full of possibilities, full of chances for the unexpected to occur. Every barrier contains within it the possibility of being crossed, every wall the potential for passage. The universe is not a clockwork machine grinding through predetermined motions, but a vast sea of potentialities, constantly exploring different possibilities, most of which follow the classical paths but some of which take the quantum road less travelled. Think about what this means for our understanding of limits and boundaries. In the classical world, if you don't have enough energy to overcome a barrier, that's it, you're stuck. The barrier is absolute. But quantum mechanics tells us that barriers are never absolutely impermeable. There's always a chance, however small, of crossing to the other side. This doesn't mean that anything is possible. The probabilities are still governed by strict mathematical laws. But it does mean that the universe has built into its very fabric a kind of flexibility, a softness at the edges of what seems impossible. The mathematics that describes quantum tunneling is surprisingly elegant. The wave function inside a barrier decays exponentially with distance, following a smooth mathematical curve. The transmission probability, the chance that a particle will tunnel through, depends on 3 main factors: the height of the barrier, how much energy would be needed to go over it classically, the width of the barrier, how thick it is, and the mass of the particle. Lighter particles tunnel more easily than heavier ones. These relationships are captured in clean mathematical equations that physicists can use to calculate tunneling probabilities with extraordinary precision. But beneath this mathematical precision lies a deeper mystery. We can calculate what will happen, we can predict the probabilities with incredible accuracy. But what is actually happening when a particle tunnels? This is where quantum mechanics becomes not just strange, but deeply philosophical. The mathematics tells us that the particle's wave function extends through the barrier. But what does this mean physically? Is the particle somehow spread out through the barrier? Is it taking all possible paths simultaneously? Is it disappearing on one side and reappearing on the other? Different interpretations of quantum mechanics give different answers to these questions, and there's no experimental way to distinguish between them. The mathematics works regardless of how we interpret it. As you rest there, perhaps feeling yourself beginning to drift, consider that you are surrounded by invisible barriers, energy walls that separate one quantum state from another. In the molecules of the air around you, electrons are confined to specific energy levels, separated by barriers of electromagnetic force. In the nuclei of atoms, protons and neutrons are held by barriers of nuclear force, and throughout all of these barriers, constantly, particles are tunneling, not many, not most, but some, enough to matter, enough to make the universe a more interesting place than it would be if classical physics were the whole story. The discovery and understanding of quantum tunneling represents one of humanity's great intellectual achievements. Here was a phenomenon that completely contradicted our everyday experience, that seemed to violate the basic principle that you can't get something for nothing, that you can't cross a barrier without having the energy to do so. Yet through careful observation, mathematical analysis, and creative thinking, physicists not only discovered that tunneling happens, but developed a precise mathematical framework for understanding and predicting it. This framework has been tested countless times over the past century and has never failed. Quantum tunneling is as real and reliable as gravity or electromagnetism. Yet despite our mathematical mastery of tunneling, despite our ability to use it in our technologies and account for it in our theories, it remains fundamentally mysterious. We can describe what happens, we can predict the outcomes, but the actual mechanism, the moment-by-moment process by which a particle moves from one side of a barrier to the other, remains hidden from us. It's as if nature has drawn a veil over the actual process, allowing us to see the before and after, but not the during. This is not a failure of our instruments or our theories. It seems to be a fundamental aspect of quantum mechanics. The transition itself is not something we can observe without destroying the very effect we're trying to see. In a sense, quantum tunneling is a perfect metaphor for the mysteries that still surround us, despite all our scientific progress. We live in an age where we can measure the universe to extraordinary precision, where we can manipulate individual atoms, where we can peer back to nearly the beginning of time itself. Yet fundamental mysteries remain. Quantum tunneling reminds us that nature still has secrets, that the universe is deeper and stranger than our everyday experience would suggest, that reality itself is more fluid and full of possibility than we might have imagined. As we continue our journey tonight, we'll explore more deeply how tunneling works, where it appears in nature and technology, and what it might tell us about the fundamental nature of reality. But for now, just rest with this image. All around you, right now, particles are quietly crossing barriers they shouldn't be able to cross. In the stars above, in the earth beneath, in the air you breathe, in the very atoms of your body, the impossible is happening. Not dramatically, not violently, but softly, probabilistically, one particle at a time. The solid world you know is shot through with quantum possibilities, riddled with tiny passages that particles can slip through when the conditions are right. And perhaps there's something comforting in this. The universe is not as rigid as it might seem. Barriers that appear absolute have soft edges. Walls that seem impermeable contain within them the possibility of passage. Nature has built flexibility into its most fundamental laws, a kind of quantum grace that allows particles to occasionally slip free from their classical constraints. In a universe governed purely by classical physics, many of the processes that make life possible would be forbidden. But we live in a quantum universe, where the impossible happens regularly, quietly, beautifully. As you drift deeper into rest, imagine yourself shrinking down to the size of an atom, down to the scale where quantum effects dominate. The solid world dissolves into clouds of probability. Barriers become regions of decreasing likelihood rather than absolute walls. Particles flow like waves, exploring all possible paths, most following the classical route, but some, always some, taking the quantum path through barriers that classical physics says cannot be crossed. This is the true texture of reality at its smallest scale, not solid and mechanical, but fluid and probabilistic, not rigid and determined, but soft and full of possibilities. The story of quantum tunneling is also a story about human curiosity and ingenuity. When physicists first encountered evidence of tunneling in radioactive decay, They could have dismissed it as experimental error or some unknown classical effect. Instead, they followed the evidence wherever it led, even when it led to conclusions that seemed absurd. They developed new mathematics to describe what they were seeing, new ways of thinking about particles and waves, energy and probability. They tested their theories with increasingly sophisticated experiments, always willing to be proven wrong, but finding instead that nature really was as strange as their equations suggested. This willingness to follow the evidence, to accept the strange and counterintuitive when that's what nature reveals, is one of science's great strengths. Quantum tunneling teaches us that our intuitions, evolved to help us navigate the macroscopic world of predators and prey, tools and shelter, are not reliable guides to how nature works at its most fundamental level. The universe is under no obligation to make sense to us, to conform to our expectations. Instead, we must conform our understanding to what the universe reveals, however strange that might be. Tonight, as we explore quantum tunneling together, we're participating in this grand human tradition of wondering about the world, of asking how things work, of being amazed by what we discover. Every civilization has wondered about the nature of reality, about what things are made of, about how the world works. We are fortunate to live in a time when we have actually found some answers, even if those answers are stranger than anything our ancestors could have imagined. Particles that tunnel through walls they can't climb over would have seemed like magic to previous generations. To us, they're a window into the quantum nature of reality. Consider the profound shift in worldview that quantum tunneling represents. For centuries, scientists and philosophers imagined the universe as a kind of vast machine, with particles as tiny billiard balls bouncing off each other according to strict mechanical laws. This view, successful as it was in explaining many phenomena, implied a universe that was fundamentally deterministic, where the future was completely determined by the past, where there was no room for genuine novelty or surprise. But quantum tunneling, along with other quantum phenomena, reveals a universe that is fundamentally probabilistic, where the future contains genuine uncertainties, where nature constantly explores multiple possibilities before settling on one. This probabilistic nature doesn't mean the universe is random or chaotic. The probabilities themselves follow strict mathematical laws. We can calculate exactly how likely a particle is to tunnel through a particular barrier, even if we can't predict whether any individual particle will tunnel or not. It's a kind of ordered uncertainty, a lawful randomness that seems to be built into the fabric of reality itself. And from this quantum uncertainty at the smallest scales emerges the largely predictable world of our everyday experience, through the law of large numbers and the averaging of countless quantum events. As you lie there, perhaps feeling your breathing slow, your thoughts beginning to soften and drift, you're a collection of roughly 10 plus 28 atoms, each one a quantum system, each one governed by the laws that allow tunneling. The vast majority of these atoms are behaving classically most of the time, their quantum nature averaged, out by their interactions with each other and their environment. But not all of them, not always. Here and there, now and then, an electron tunnels through a barrier in one of your molecules, a proton transfers from one site to another through quantum tunneling. A small quantum event occurs that would be impossible in a purely classical world. These quantum events in your body are not accidents or errors. They're part of how you work. Evolution has had billions of years to explore the possibilities offered by quantum mechanics, and life has incorporated quantum effects into its basic operations. Some researchers even suggest that consciousness itself might involve quantum processes, though this remains highly speculative and controversial. What's certain is that you're not just a classical being living in a quantum world. You're a quantum being through and through, your very existence dependent on phenomena like tunneling that classical physics cannot explain. The gentle dance of particles tunneling through barriers continues all around us, a constant quiet background to everything that happens in the universe. In the rocks beneath us, radioactive atoms decay through tunneling, their alpha particles escaping nuclear prisons to begin new existences as helium atoms. In the atmosphere above us, chemical reactions proceed with the help of tunneling, particles crossing energy barriers to form new molecules. In the vast spaces between stars, even in the cold near vacuum of interstellar space, tunneling allows chemical reactions to occur that would be impossible classically, slowly building the complex molecules that will one day be incorporated into new stars and planets. And in the electronic devices that surround us, that have become so integral to modern life. Tunneling is deliberately harnessed and controlled. Every time you save a file on a flash drive, electrons tunnel through barriers to store your information. Every time scientists use a scanning tunneling microscope to image individual atoms, they're measuring the current of electrons tunneling between a metal tip and a surface. Quantum tunneling has moved from an abstract phenomenon that puzzled physicists to a practical tool that engineers use to build better devices. But perhaps the most remarkable place where tunneling occurs is in the stars, those distant suns that light the night sky. Each star is a vast fusion reactor, converting hydrogen into helium and releasing enormous amounts of energy in the process. But for fusion to occur, protons must get close enough together for the strong nuclear force to overcome their electromagnetic repulsion. The temperature even in stellar cores is not high enough for protons to have sufficient energy to overcome this repulsion classically. They need quantum tunneling to bridge the gap, to cross the barrier that keeps them apart. Without tunneling, stars would not shine, or at least not in the steady, long-lasting way they do. They might undergo brief explosive fusion events, but they couldn't sustain the steady fusion reactions that power them for billions of years. Our sun has been shining steadily for about 4.5 billion years, and will continue for billions more, all thanks to the quiet, persistent tunneling of protons in its core. Every photon of sunlight that reaches Earth, every bit of warmth you feel on your skin on a sunny day, exists because particles in the sun's core are tunneling through barriers they don't have enough energy to cross classically. This connection between quantum tunneling and stellar fusion means that tunneling is not just some abstract quantum phenomenon, but something directly connected to our existence. The energy that powers all life on Earth ultimately comes from the sun, and the sun's energy comes from fusion reactions made possible by tunneling. The carbon atoms in your body, the oxygen you breathe, the iron in your blood, all of these elements heavier than hydrogen were forged in the cores of stars through fusion reactions that required tunneling. We are, in a very real sense, children of quantum tunneling, our very atoms owing their existence to particles that crossed barriers they shouldn't have been able to cross. As we prepare to move deeper into our exploration, to examine more closely the experimental evidence for tunneling and what it tells us about reality, take a moment to appreciate the profound beauty of what we've discovered so far. The universe is not the rigid mechanical system that classical physics suggested. It's something far more subtle, far more interesting. At its foundation lies a kind of quantum flexibility that allows particles to explore possibilities that classical physics would forbid. This flexibility doesn't make the universe chaotic or unpredictable. Instead, it makes it rich with possibilities, full of phenomena that a purely classical universe could never support. The walls and barriers that seem so solid and absolute in our everyday experience are, at the quantum level, more like probability gradients, regions where existence becomes less likely but never impossible. A particle approaching such a barrier doesn't simply bounce off. Its quantum wave explores the barrier, penetrates into it, and sometimes, just sometimes, emerges on the other side. This is not magic or mysticism. It's the actual way nature works at its most fundamental level, confirmed by countless experiments and essential to technologies we use every day. And so, as you rest there, surrounded by the quiet darkness, know that you are immersed in a sea of quantum phenomena. Particles are tunneling all around you and within you, crossing barriers that classical physics says cannot be crossed, making possible phenomena that a purely classical universe could never support. You're not separate from this quantum world. You are part of it, made of it, sustained by it. Every atom in your body, every molecule, every chemical reaction that keeps you alive is governed by quantum laws that allow for tunneling and other phenomena that transcend classical limitations. The discovery of quantum tunneling and our growing understanding of it represents one of humanity's great intellectual adventures. Starting from puzzling observations about radioactive decay, physicists developed an entirely new way of understanding reality, one that revealed the probabilistic, wave-like nature of matter at its smallest scales. This understanding has not only solved scientific puzzles, but has led to practical technologies that have transformed our world. And perhaps most importantly, it has shown us that nature is far stranger and more wonderful than we might have imagined. And now, as we drift deeper into this quantum realm, let's return to our central question with fresh eyes. approaching it from different angles, like walking around a sculpture in soft light, seeing how it changes as our perspective shifts. Why can particles tunnel through walls they don't have energy to cross? The question itself seems to contain a contradiction, doesn't it? It's like asking why something impossible is possible, why the rules can be broken while still being followed. Yet this is exactly what nature does at the quantum scale, constantly, quietly, everywhere. Let's think about this more carefully, more slowly, letting the strangeness of it really sink in. In our everyday world, the world of classical physics that our intuitions are built for, energy is needed to overcome barriers. This is such a fundamental principle that we rarely even think about it consciously. If you want to throw a ball over a wall, you need to give it enough kinetic energy to reach the top of the wall. If you want to push a cart up a hill, you need to exert enough force to give it the potential energy to reach the summit. If you don't have enough energy, you simply can't get to the other side. This is not just a practical limitation. In classical physics, it's an absolute law. Energy is conserved, and you can't get to a higher energy state without adding energy from somewhere. But imagine now that we shrink down past the scale of cells, past molecules, down to individual atoms and the particles that compose them. Here, in this quantum realm, something remarkable happens to our understanding of particles and energy. The particle is no longer a tiny solid sphere with a definite position and momentum. Instead, it becomes something more like a cloud, a wave, a spreading pattern of possibility. This is not just a metaphor or a visualization trick. This wave nature is the fundamental reality of quantum particles. When we're not measuring a particle's position, it doesn't have a definite position. It exists as a wave function, a mathematical entity that describes the probability of finding the particle at different locations if we were to measure it. This wave function, this probability cloud, behaves like a wave in many respects. It can interfere with itself, creating patterns of high and low probability. It can diffract around obstacles, spreading out after passing through narrow openings. And crucially for our story tonight, when it encounters a barrier, it doesn't stop abruptly at the barrier's edge. Instead, like a water wave hitting a seawall, part of it penetrates into the barrier, though it weakens rapidly as it goes deeper. This penetration is not a violation of energy conservation. The wave function inside the barrier represents a kind of virtual state, a temporary quantum fluctuation that doesn't violate any fundamental laws as long as it doesn't persist indefinitely. To understand this better, let's use an analogy that might help make this abstract concept more tangible. Imagine you're in a quiet room, and there's a thick wall separating you from another room where music is playing. Classical physics would say that if the sound waves don't have enough energy to break through the wall, no sound should reach you. But we know from experience that this isn't quite true. Some sound does penetrate the wall, though it's much quieter on your side. The sound waves don't stop abruptly at the wall's surface. They penetrate into it, losing energy as they go, and if the wall is thin enough, some sound emerges on the other side, weakened but still present. Quantum tunneling is similar in some ways, though the analogy isn't perfect. When a quantum particle's wave function encounters a barrier, it penetrates into the barrier, decreasing exponentially with distance. This exponential decay is rapid. The wave function might decrease by a factor of 10 for every nanometer it penetrates into the barrier, depending on the specific conditions. But exponential decay, rapid as it is, never quite reaches zero. There's always some tiny, vanishingly small but non-zero amplitude of the wave function that extends through the barrier, no matter how thick it is. And if the barrier is thin enough, this amplitude on the far side can be significant enough that there's a reasonable probability of finding the particle there. Now you might be wondering, if the particle doesn't have enough energy to be inside the barrier classically, how can its wave function exist there at all? This is where quantum mechanics diverges most dramatically from classical physics. In quantum mechanics, particles can temporarily exist in states that would be energetically forbidden classically, as long as these states don't persist for too long. This is related to the famous Heisenberg uncertainty principle, which tells us that energy and time have a fundamental uncertainty relationship. For very short times, energy conservation can appear to be violated, though it's always restored when we look at longer timescales. The wave function inside the barrier represents just such a temporary virtual state. The mathematics that describes this process is beautifully elegant. The wave function inside a barrier is described by an exponential function, one of the most fundamental mathematical forms in nature. Exponential functions appear everywhere in physics, from radioactive decay to the absorption of light in materials, from population growth to the cooling of hot objects. There's something deeply satisfying about finding the same mathematical form describing such diverse phenomena, as if nature has a preference for certain mathematical patterns. The transmission probability for a particle to tunnel through a barrier depends on several factors, and understanding these factors helps us grasp when tunneling is likely to be important and when it can be ignored. First, there's the height of the barrier, which is the difference between the barrier's energy and the particle's energy. The greater this difference, the less likely tunneling becomes. If a particle has almost enough energy to go over the barrier classically, tunneling is relatively likely. If it has much less energy than needed, tunneling becomes exponentially less probable. Second, there's the width of the barrier. This is perhaps the most critical factor. The tunneling probability decreases exponentially with barrier width, which means that even small increases in width can dramatically reduce the chance of tunneling. A barrier that's twice as thick might have a tunneling probability that's not just half as much but perhaps 1,000th or 1,000,000th as much depending on the other parameters. This exponential dependence on width is why tunneling is typically only important for very thin barriers, usually on the scale of nanometers or less. Third, there's the mass of the particle. Lighter particles tunnel more easily than heavier ones. This is why electron tunneling is much more common than proton tunneling, and why tunneling of entire atoms is extremely rare except under very special conditions. The wave function of a heavy particle decays more rapidly inside a barrier than that of a light particle, making it much less likely to extend all the way through. This mass dependence is one reason why quantum effects are generally more noticeable for electrons than for atomic nuclei, and why quantum mechanics seems less relevant for everyday objects, which are vastly heavier still. Let's think about this in terms of specific examples to make it more concrete. Consider an electron approaching an energy barrier in a semiconductor device. The electron might have an energy of, say, 1 electron volt, while the barrier might be 2 electron volts high. Classically, the electron cannot cross this barrier. It would need twice as much energy. But if the barrier is only a few nanometers thick, there might be a 1% chance that the electron tunnels through. Make the barrier twice as thick and the probability might drop to 0.1%. Make it 3 times as thick and we're down to 0.0%. The probability falls off incredibly quickly with barrier width. Now consider a proton facing a similar barrier. The proton is about 2,000 times heavier than the electron, and this makes an enormous difference. For the same barrier that gave the electron a 1% tunneling probability, the proton might have a probability of only 0 to 0% or even less. The exact number would depend on the specific parameters, but the point is that the heavier particle has a vastly lower tunneling probability. This is why proton tunneling, while it does occur and is important in some contexts, is much rarer than electron tunneling. But here's where things get interesting. Even though the probability of any individual particle tunneling might be tiny, if you have enough particles and enough time, tunneling events will occur. In a piece of radioactive uranium, there are roughly 10 to the 24 atoms. Even if the probability of any individual alpha particle tunneling out of its nucleus in a given second is incredibly tiny, say 1 in 1020, that still means thousands of decay events per second in a gram of material. This is how radioactive decay works, not through any external trigger or cause, but through the patient probabilistic process of particles tunneling through nuclear barriers. The discovery that tunneling could explain radioactive decay was a triumph of quantum mechanics, but it also raised deep philosophical questions that we're still grappling with today. If tunneling is a purely probabilistic process, if there's no way to predict when any individual particle will tunnel, what does this say about the nature of reality? Is the universe fundamentally random at its base? Or is there some deeper level of reality, some hidden variables that determine when tunneling will occur that we simply haven't discovered yet? Different physicists and philosophers have different views on these questions. The standard Copenhagen interpretation of quantum mechanics, developed by Niels Bohr and others, says that the probabilistic nature of tunneling is fundamental. There's no deeper level that determines when a particle will tunnel. It's genuinely random within the constraints of the probability distributions. Einstein famously disagreed with this view, saying that God does not play dice with the universe, but decades of experiments have failed to find any hidden variables that could make quantum mechanics deterministic. Other interpretations offer different perspectives. The many worlds interpretation suggests that every time a tunneling event could occur, the universe splits into branches where it did and didn't happen, with all possibilities being realized in parallel universes. The de Broglie-Bohm interpretation proposes that particles have definite positions at all times, guided by a pilot wave that determines their motion, including when they tunnel. Each interpretation gives the same mathematical predictions, so there's no experimental way to distinguish between them, at least not with current technology. But regardless of how we interpret it philosophically, the practical reality of tunneling is undeniable. We can measure it, we can use it, we can rely on it. Modern technology is full of devices that depend on tunneling being a real, reliable phenomenon. The scanning tunneling microscope, invented in the 1980s, uses the exponential dependence of tunneling on distance to image surfaces with atomic resolution. By measuring how the tunneling current between a sharp metal tip and a surface changes as the tip scans across the surface, scientists can map out the positions of individual atoms. Flash memory, the technology that stores data in everything from USB drives to solid-state hard drives, relies on electrons tunneling through a thin insulating barrier to store and erase information. When you save a file, electrons tunnel through the barrier and become trapped on the other side, where they can remain for years. When you delete the file, a voltage is applied that allows the electrons to tunnel back. The reliability of modern flash memory depends on our precise understanding of how tunneling probability depends on barrier thickness and applied voltage. Even the humble tunnel diode, invented in the 1950s, exploits quantum tunneling to create a device with unique electrical properties. In a tunnel diode, electrons can tunnel through the junction between two types of semiconductor material, creating a current-voltage relationship that's impossible to achieve with classical devices. Tunnel diodes can switch faster than conventional diodes and can operate at very low voltages, making them useful in certain specialized applications. As we contemplate these practical applications, it's worth reflecting on how remarkable it is that we've learned to harness such a fundamentally quantum phenomenon. Tunneling seems like it should be some exotic effect that only matters in extreme conditions, yet we've incorporated it into devices that billions of people use every day. Your smartphone probably contains billions of transistors, many of which involve tunneling effects. The computer you might use for work relies on memory chips that use tunneling to store data. We've taken one of nature's strangest phenomena and made it mundane, practical, essential to modern life. But let's return to the deeper mystery of what's actually happening when a particle tunnels. The mathematics tells us that the wave function extends through the barrier, but what does this mean physically? One way to think about it is that the particle is exploring all possible paths simultaneously, including paths that go through the barrier. Most of these paths have very low probability, but they all contribute to the final outcome. This is the path integral formulation of quantum mechanics, developed by Richard Feynman, which describes quantum processes as sums over all possible paths, weighted by their probabilities. In this view, a particle doesn't take a single, definite path from one side of the barrier to the other. Instead, it takes all possible paths, simultaneously existing in a superposition of different trajectories until a measurement forces it to choose one. Some of these paths go over the barrier, some go around it if that's possible, and some go straight through it. The paths that go through the barrier contribute less to the final probability because they require the particle to exist in classically forbidden states, but they still contribute something, and sometimes, when all the quantum amplitudes are added up, the particle ends up on the far side of the barrier. Another way to think about tunneling is in terms of the uncertainty principle. The uncertainty principle tells us that we cannot simultaneously know a particle's position and momentum with perfect precision. The more precisely we know where a particle is, the less precisely we know how fast it's moving, and vice versa. This isn't just a limitation of our measuring instruments, it's a fundamental aspect of quantum reality. The particle doesn't have a perfectly defined position and momentum simultaneously. This uncertainty creates a kind of quantum fuzziness that allows tunneling to occur. When a particle is near a barrier, its position uncertainty means it's not entirely on one side or the other. There's some probability amplitude on both sides, and if conditions are right, the particle can be found on the far side even though it never had enough energy to go over the barrier. It's as if the uncertainty principle creates tiny quantum fluctuations that occasionally allow particles to slip through barriers that should be impermeable. Yet another perspective comes from thinking about energy-time uncertainty. The uncertainty principle also applies to energy and time. The shorter the time interval we consider, the greater the uncertainty in energy. For very brief moments, a particle can borrow energy from the quantum vacuum, existing in a higher energy state than it should classically be able to achieve. If it can borrow enough energy for long enough to cross the barrier, it might find itself on the other side. Of course, it has to pay back this borrowed energy, but by then it's already through the barrier. These different ways of thinking about tunneling, path integrals, position uncertainty, energy-time uncertainty are not contradictory. They're different perspectives on the same quantum mechanical phenomenon, different ways of visualizing or understanding what the mathematics is telling us. The mathematics itself is unambiguous and incredibly successful at predicting experimental results. But the physical interpretation, the story we tell ourselves about what's really happening, remains open to different perspectives. What all these perspectives share is the recognition that tunneling is not a violation of physical laws but a consequence of them. When we properly account for the quantum nature of particles, when we recognize that particles are waves as well as particles, when we include the uncertainty, principle and the probabilistic nature of quantum mechanics, tunneling emerges naturally from the equations. It's not an exception or an anomaly. It's what the laws of quantum mechanics predict should happen. As you lie there, perhaps feeling your thoughts beginning to soften and blend together like quantum waves interfering with each other, consider how tunneling challenges our very notion of what a barrier is. In the classical world, a barrier is something that stops motion, that prevents passage from one region to another. But in the quantum world, a barrier is more like a filter, reducing but not eliminating the probability of passage. Every barrier is porous at the quantum level. Every wall has some transparency to quantum waves. This porosity of quantum barriers has profound implications for how we understand the stability of matter itself. Atomic nuclei are held together by the strong nuclear force, which creates a barrier that keeps protons and neutrons confined. But this barrier is not absolute. Through tunneling, particles can escape, leading to radioactive decay. The stability of any atomic nucleus is not absolute but probabilistic. Even nuclei that we consider stable, like carbon-12 or oxygen-16, have some infinitesimally small probability of decay through tunneling. The probability is so small that the expected lifetime is many, many times longer than the age of the universe, but it's not infinite. Similarly, electrons in atoms are confined by electromagnetic barriers, held in orbit around nuclei by the attraction between negative and positive charges. But these barriers too are not absolute. Electrons can tunnel from one atom to another, especially when atoms are close together in molecules or solids. This electron tunneling is crucial for many chemical reactions and for electrical conduction in materials. The very fact that materials can conduct electricity depends on electrons being able to tunnel between atoms. The softness of quantum barriers extends even to seemingly empty space itself. In quantum field theory, even the vacuum is not truly empty but filled with quantum fluctuations, virtual particles that pop into existence and disappear again. These fluctuations can be thought of as particles tunneling into existence from nothing, borrowing energy from the vacuum for brief moments before paying it back and vanishing again. This quantum vacuum energy has real, measurable effects, such as the Casimir effect, where two metal plates placed very close together are pushed together by the difference in vacuum fluctuations inside and outside the gap between them. As we delve deeper into the implications of tunneling, we begin to see that it's not just one quantum phenomenon among many, but a window into the fundamental quantum nature of reality. The fact that particles can tunnel through barriers they don't have energy to cross tells us that the universe is not the deterministic mechanical system that classical physics portrayed. Instead, it's a realm of possibilities and probabilities, where the impossible can happen, just rarely, and where the boundary between what is and what might be is always slightly blurred. Think about what this means for causation and determinism. In classical physics, if you know the exact state of a system at one moment, you can in principle calculate its exact state at any future moment. The future is completely determined by the present. But tunneling introduces genuine randomness into the universe. Even if you know everything about a particle approaching a barrier, you cannot predict with certainty whether it will tunnel through or not. You can only calculate probabilities. This means the future is not completely determined by the present. There's genuine openness, genuine possibility for different outcomes. This indeterminacy might seem troubling at first. We like to think of the universe as orderly and predictable, governed by strict laws of cause and effect. And indeed, at the macroscopic scale, quantum indeterminacy usually averages out to give us the predictable world we experience. But at the microscopic scale, and occasionally even at larger scales, quantum indeterminacy matters. Every radioactive decay, every tunneling event in your body's chemistry, every quantum transition in the atoms around you introduces a tiny element of genuine randomness into the world. But perhaps there's something liberating about this quantum indeterminacy. It means the future is not a fixed destination that we're helplessly moving toward, but a landscape of possibilities that's constantly being explored and decided. Every quantum event is a tiny choice point where the universe could go one way or another. Most of these choices are inconsequential, averaging out to give us the stable, predictable world we know, but some of them matter, cascading up through the scales to influence larger events. Consider, for instance, cosmic rays, high-energy particles that stream through space and occasionally strike Earth's atmosphere. When a cosmic ray particle hits an atom in the atmosphere, it can trigger a cascade of secondary particles, some of which reach the ground. These particles can cause quantum tunneling events in electronic devices, potentially flipping bits in computer memory. Usually, error correction systems catch and fix these errors, but occasionally one might slip through, causing a calculation to go wrong or a program to crash. A quantum tunneling event triggered by a particle from a distant supernova could, in principle, influence events on Earth. Or consider the role of tunneling in biological mutations. DNA replication is remarkably accurate, but it's not perfect. Sometimes, quantum tunneling can cause a proton to shift position in a DNA base, changing its chemical properties and potentially leading to a mutation. Most mutations are harmless or harmful, but occasionally one might be beneficial, giving an organism a survival advantage. Over evolutionary time, these quantum events can influence the course of life on Earth. We are in part products of countless quantum tunneling events that occurred in the DNA of our ancestors. As we continue to explore the soft puzzle of quantum tunneling, we see that it's not just a curious anomaly, but a fundamental feature of how the universe works at its smallest scales. It's a phenomenon that bridges the quantum and classical worlds, that enables processes essential to life and technology, that introduces genuine indeterminacy into the fabric of reality. And perhaps most remarkably, it's a phenomenon that we've learned to understand, predict, and even harness, despite its fundamental strangeness. The equations that describe tunneling, derived from the Schrödinger equation that governs quantum mechanics, are some of the most tested and validated in all of physics. We can calculate tunneling probabilities to extraordinary precision, and experiments confirm these calculations again and again. The same equations that describe electron tunneling in a laboratory device also describe proton tunneling in the sun's core, alpha particle tunneling in radioactive decay, and even more exotic tunneling processes in particle physics experiments. The universality of these equations, their ability to describe such diverse phenomena with the same mathematical framework, is a testament to the deep unity underlying physical reality. Yet despite our mathematical mastery of tunneling, despite our ability to calculate and predict it, something mysterious remains. The moment of tunneling itself, the actual transition from one side of the barrier to the other, remains hidden from direct observation. We can detect a particle on one side of a barrier and later detect it on the other side, but we cannot watch the tunneling process itself without disturbing it. Any attempt to observe a particle while it's tunneling would require interacting with it in a way that would disrupt the tunneling process. The transition itself remains veiled, a quantum secret that nature keeps from our direct observation. This limitation is not just a practical problem that might be solved with better instruments. It seems to be a fundamental aspect of quantum mechanics, related to the measurement problem that lies at the heart of quantum theory. When we're not observing a quantum system, it evolves according to the Schrödinger equation, existing in superpositions of different states. But when we make a measurement, the system appears to collapse into a definite state. How and why this collapse occurs, and what it means for the nature of reality, remains one of the deepest unsolved problems in physics. Tunneling exemplifies this measurement problem beautifully. When a particle approaches a barrier, its wave function spreads out, developing components on both sides of the barrier. The particle exists in a superposition of having tunnelled and not having tunnelled. Only when we make a measurement do we find the particle definitely on one side or the other. But what causes this transition from superposition to definite outcome? Is it consciousness? Is it interaction with the environment? Is it something else entirely? We don't know, and tunnelling, common as it is, constantly confronts us with this mystery. As you rest there, perhaps feeling yourself beginning to drift like a quantum wave spreading out through space, consider how remarkable it is that we're able to contemplate these questions at all. We are collections of atoms, governed by quantum mechanics, that have somehow developed the ability to discover and understand quantum mechanics. We are the universe becoming aware of its own quantum nature, using quantum processes in our brains to think about quantum processes in the world around us. The story of how humanity discovered quantum tunnelling is itself a fascinating journey of scientific discovery. In the early 20th century, physicists were confronted with phenomena that classical physics simply couldn't explain. Radioactive decay was one of the most puzzling. Here were atoms spontaneously ejecting particles with no apparent cause or trigger. The energy involved suggested that these particles were escaping from deep potential wells that they shouldn't be able to climb out of. It was as if prisoners were escaping from a deep pit without ladders or ropes. The solution came from applying the newly developed quantum mechanics to the problem. George Gamow, a young Russian physicist working in Germany, realized that if particles were described by waves, as quantum mechanics suggested, then these waves could extend beyond classical barriers. He calculated the probability of alpha particles tunneling out of nuclei and found that his calculations matched the observed decay rates. It was a stunning confirmation of quantum mechanics and the first clear evidence that tunneling was a real physical phenomenon. But the implications went far beyond explaining radioactive decay. Once physicists understood that tunneling was possible, they began to see its fingerprints everywhere. It explained why certain chemical reactions could occur at temperatures where they shouldn't be possible classically. It explained the electrical properties of certain materials and devices. It even explained how the sun could shine steadily for billions of years, as Hans Bethe and others showed that stellar fusion depends critically on proton tunneling. Today, our understanding of tunneling has progressed far beyond those early discoveries. We can engineer materials and devices that exploit tunneling in precisely controlled ways. We can use tunneling to probe the quantum properties of individual atoms and molecules. We can even use tunneling to create quantum computers, devices that harness quantum superposition and entanglement to perform calculations that would be impossible for classical computers. Yet in some ways, tunneling remains as mysterious as ever. We understand the mathematics perfectly, we can predict and control it with extraordinary precision, but the deeper questions about what it means for the nature of reality remain open. Is the universe fundamentally probabilistic, or is there some deeper deterministic layer we haven't discovered? What does it mean for a particle to be in two places at once? How does the classical world emerge from the quantum? These questions, raised by phenomena like tunneling, continue to challenge and inspire physicists and philosophers. As we prepare to move on to examine the experimental evidence for tunneling in more detail, let's pause to appreciate the beautiful strangeness of what we've discovered. Particles can cross barriers they don't have energy to climb over. They do this not by breaking the laws of physics, but by following them, by being waves as well as particles, by existing in superpositions of different states, by exploring all possible paths simultaneously. This is not science fiction or fantasy. It's the actual way nature works at its most fundamental level. And this quantum tunneling is not some rare exotic phenomenon that only happens in physics laboratories. It's happening constantly, everywhere, in the stars above and the earth below, in the air you breathe and the atoms of your body. It's essential to the nuclear processes that created the elements, to the chemistry that sustains life, to the technologies that define modern civilization. We live in a universe where the impossible happens regularly, where barriers are suggestions rather than absolutes, where particles can be on both sides of a wall at once, until observation forces them to choose. In the hushed spaces of laboratories around the world, in the deep quiet of the night when most people are sleeping, scientists conduct experiments that probe the quantum nature of reality. These are not dramatic experiments with sparks flying and machines humming loudly. They are subtle, delicate investigations that require extraordinary precision and patience. They are attempts to catch nature in the act of doing something that shouldn't be possible, to measure and quantify the impossible, to turn the mystery of quantum tunneling into precise, reliable science. Let's begin with the story of radioactive decay, the phenomenon that first revealed tunneling to human understanding. In the early years of the 20th century, scientists like Ernest Rutherford and Marie Curie were studying radioactive elements, materials that spontaneously emitted particles and energy. They found that certain heavy atomic nuclei would occasionally eject alpha particles, which are essentially helium nuclei consisting of 2 protons and 2 neutrons bound together. What puzzled them was the energy of these alpha particles. They were escaping from the nucleus with far less energy than should be needed to overcome the nuclear force holding them in place. Imagine the nucleus as a valley surrounded by high walls. The alpha particle sits in this valley, held there by the strong nuclear force. To escape classically, it would need enough energy to climb to the top of the wall. But the alpha particles being emitted had only a fraction of this energy. It was as if they were somehow passing through the wall rather than over it. For years, this remained a mystery, a phenomenon that seemed to violate the conservation of energy, one of the most fundamental principles in physics. The solution came in 1928 when George Gamow applied the newly developed mathematics of quantum mechanics to the problem. He realized that if the alpha particle was described by a quantum wave function, this wave wouldn't stop abruptly at the nuclear wall but would extend into and through it, decreasing exponentially with distance. If the wall was thin enough, there would be some probability of finding the alpha particle outside the nucleus, even though it never had enough energy to climb over the wall classically. Gamow calculated these probabilities and found they matched the observed decay rates with remarkable precision. This was more than just a theoretical triumph. It was a demonstration that quantum mechanics wasn't just an abstract mathematical framework, but a description of real physical processes happening in nature. The agreement between Gamow's calculations and experimental measurements was too good to be coincidence. Nature really was allowing particles to tunnel through barriers they couldn't classically cross. The impossible was not only possible, but measurable and predictable. Following Gamow's success, physicists began looking for other examples of tunneling, and they found them everywhere. In 1957, Leo Esaki discovered what came to be called the tunnel diode while working at Sony in Japan. He was investigating the electrical properties of heavily doped germanium PN junctions when he noticed something unusual. At very low voltages, current was flowing through the junction, even though there shouldn't be enough energy for electrons to cross the barrier between the p-type and n-type regions. The electrons were tunneling through the barrier. What made Esaki's discovery particularly significant was that it showed tunneling wasn't just some exotic nuclear phenomenon, but something that could occur in ordinary electronic devices at room temperature. The tunnel diode had unique electrical properties that couldn't be achieved with conventional devices. As voltage increased, the tunneling current would first increase, then decrease, then increase again, creating a region of negative resistance where increasing voltage led to decreasing current. This unusual behavior made tunnel diodes useful for high-frequency oscillators and amplifiers, and Esaki's discovery earned him the Nobel Prize in Physics in 1973. But perhaps the most elegant demonstration of tunneling came with the invention of the scanning tunneling microscope in 1981 by Gerd Binnig and Heinrich Rohrer at IBM's Zurich Research Laboratory. They realized that the exponential dependence of tunneling probability on distance could be used to create an extraordinarily sensitive probe of surfaces. By bringing a sharp metal tip very close to a conducting surface and measuring the tunneling current between them, they could map out the surface with atomic resolution. The principle is beautifully simple. When the tip is brought within about a nanometer of the surface, electrons can tunnel between the tip and the surface, creating a small current. This current depends exponentially on the distance between tip and surface. Moving the tip just 1/10 of a nanometer closer might increase the current by a factor of 10. By scanning the tip across the surface and adjusting its height to maintain a constant tunneling current, scientists can map out the atomic landscape of the surface with incredible precision. The first images from scanning tunneling microscopes were revelatory. For the first time, humans could see individual atoms, not as abstract mathematical points, but as real objects with definite positions and shapes. The images showed the regular arrays of atoms in crystal surfaces, the steps and defects where the crystal structure was imperfect, even individual foreign atoms sitting on the surface. It was like suddenly being able to see the individual bricks in a wall, that had previously looked smooth and featureless. The scanning tunneling microscope didn't just allow scientists to see atoms, it allowed them to manipulate them. By adjusting the voltage between tip and surface, scientists could pick up individual atoms, move them to new positions and set them down again. In 1989, scientists at IBM used a scanning tunneling microscope to spell out IBM using 35 individual xenon atoms on a nickel surface. It was the world's smallest logo, a demonstration of humanity's ability to control matter at the atomic scale, all made possible by quantum tunneling. These experimental triumphs were accompanied by increasingly sophisticated theoretical understanding. Physicists developed methods to calculate tunneling probabilities for complex barriers of different shapes, not just simple rectangular walls. They found that the transmission probability could be enhanced at certain energies, a phenomenon called resonant tunneling, where the particle's wave interferes constructively with itself to increase the chance of transmission. They discovered that tunneling times, the duration of the tunneling process itself, were surprisingly subtle to define and measure, leading to ongoing debates about what it means for a particle to spend time inside a classically forbidden region. In the 1960s, Brian Josephson, then a graduate student at Cambridge University, predicted that pairs of electrons could tunnel through an insulating barrier between two superconductors, creating what's now called a Josephson junction. This wasn't just single electrons tunneling, but Cooper pairs, the bound pairs of electrons that carry current in superconductors without resistance. Josephson predicted that this tunneling would lead to remarkable effects. A DC current could flow through the junction with no voltage applied, and an AC current would flow if a constant voltage was applied. These predictions seemed almost too strange to be true, but experiments quickly confirmed them. Josephson junctions turned out to have extraordinary properties. They could detect incredibly small magnetic fields, measure voltages with unprecedented precision, and generate microwave radiation with very precise frequencies. Today, Josephson junctions are used in SQUIDs, superconducting quantum interference devices, the most sensitive magnetometers known, capable of detecting the tiny magnetic fields produced by neural activity in the brain. They're also used in voltage standards, providing the most precise way to measure and define the volt. As experimental techniques improved, scientists began to observe tunneling in increasingly diverse contexts. In chemistry, they found that proton tunneling could dramatically affect reaction rates, especially at low temperatures. The transfer of hydrogen atoms in certain enzymatic reactions was found to involve significant tunneling, with the light hydrogen nucleus quantum mechanically crossing energy barriers rather than going over them thermally. This discovery revolutionized our understanding of enzyme catalysis and showed that life itself depends on quantum tunneling. In the 1990s, experiments with ultra-cold atoms opened up new ways to study tunneling. By cooling atoms to within billionths of a degree of absolute zero and trapping them in optical lattices created by interfering laser beams, scientists could create artificial crystals where they could watch individual atoms tunnel between lattice sites. These experiments allowed unprecedented control over tunneling processes, letting scientists adjust barrier heights and widths in real time and observe how tunneling rates changed in response. One particularly beautiful experiment involved creating a Bose-Einstein condensate, a state of matter where thousands of atoms occupy the same quantum state and behave as a single quantum entity. When such a condensate is placed in a double well potential, essentially two valleys separated by a barrier, the entire condensate can tunnel back and forth between the wells, oscillating like a quantum pendulum. This is macroscopic quantum tunneling, where thousands of atoms tunnel together as a single quantum object, making the quantum phenomenon visible on an almost macroscopic scale. Flash memory, the technology that stores data in USB drives, solid-state drives, and memory cards, provides perhaps the most widespread practical application of tunneling. In flash memory, information is stored by trapping electrons on floating gates, isolated islands of conductor surrounded by insulating material. To write data, a high voltage is applied that allows electrons to tunnel through the insulator onto the floating gate, where they become trapped. To erase data, the voltage is reversed, allowing the electrons to tunnel back out. The reliability of flash memory depends on the insulator being thick enough that electrons don't tunnel out spontaneously, but thin enough that they can tunnel through when desired. The development of flash memory required exquisite control over tunneling probabilities. The insulating layers are typically just a few nanometers thick, and their exact thickness determines how long data can be retained and how many write-erase cycles the memory can endure. Too thin, and data is lost quickly as electrons tunnel out spontaneously. Too thick, and the high voltages needed for writing and erasing damage the insulator. Modern flash memory represents a triumph of engineering, with billions of tiny tunneling barriers working reliably to store our digital lives. Recent experiments have pushed our ability to observe and control tunneling to new extremes. Using ultra-fast laser pulses, scientists can now watch tunneling happen in real time, or at least as close to real time as the uncertainty principle allows. These attosecond spectroscopy experiments, using laser pulses lasting just billionths of a second, can capture the moment when an electron tunnels out of an atom in a strong electric field. The results have confirmed quantum mechanical predictions, while also revealing subtle details about the tunneling process that continue to challenge our understanding. In particle physics, tunneling plays a crucial role in understanding the fundamental forces and particles that make up our universe. The production of particle-antiparticle pairs from the quantum vacuum in strong electric fields, known as the Schwinger effect, is essentially a tunneling process where particles tunnel into existence from nothing. Though the electric fields required are enormous, far beyond what we can currently produce in laboratories, this process is thought to occur near black holes and may have been important in the early universe. Perhaps most remarkably, there's growing evidence that tunneling might play a role in biological processes beyond enzyme catalysis. Some researchers have suggested that quantum tunneling of electrons might be involved in photosynthesis, helping to explain the remarkable efficiency with which plants convert sunlight into chemical energy. Others have proposed that proton tunneling in DNA base pairs could contribute to genetic mutations, making quantum mechanics partly responsible for the genetic variation that drives evolution. While these ideas remain controversial and are subjects of ongoing research, they suggest that life itself might be more quantum mechanical than we previously thought. The experimental evidence for tunneling is now so overwhelming, so diverse, and so precisely quantified that there's no doubt about its reality. We can measure tunneling currents with extraordinary precision, predict tunneling rates with remarkable accuracy, and engineer devices that exploit tunneling in exactly the ways we intend. The agreement between theoretical predictions and experimental measurements is often good to 10 or more decimal places, making quantum tunneling one of the most precisely tested phenomena in all of physics. Yet despite this experimental mastery, certain aspects of tunneling remain elusive. The tunneling time problem, for instance, continues to generate debate and new experiments. How long does a particle spend inside a barrier while tunneling? Some experiments suggest the transit time is nearly instantaneous, regardless of barrier width, while others indicate a finite delay. The question is complicated by the fact that measuring a particle while it's inside the barrier would disturb the tunneling process, making direct observation impossible. It's a reminder that even well-understood quantum phenomena can harbour deep mysteries. Another ongoing area of investigation is the role of the environment in tunneling processes. Real quantum systems are never perfectly isolated. They're always interacting with their surroundings to some degree. These interactions can suppress tunneling through a process called decoherence, where the quantum superposition necessary for tunneling is destroyed by environmental disturbance. Understanding and controlling decoherence is crucial for quantum technologies like quantum computers, where we need to maintain quantum superpositions long enough to perform calculations. Scientists are also exploring ways to enhance or suppress tunneling for practical applications. Resonant tunneling devices use quantum interference effects to create sharp peaks in tunneling probability at specific energies, useful for creating highly selective filters and detectors. Quantum dots, tiny islands of semiconductor that confine electrons in all three dimensions, use tunneling barriers to create artificial atoms with tunable properties. These technologies represent just the beginning of our ability to engineer quantum systems for specific purposes. The study of tunneling has also revealed deep connections between different areas of physics. The mathematics that describes quantum tunneling is closely related to that describing classical wave phenomena, like frustrated total internal reflection, where light can tunnel through air gaps between prisms. It's also connected to instantons in quantum field theory, mathematical objects that describe tunneling between different vacuum states. These connections suggest that tunneling is not just a quirk of quantum mechanics, but a manifestation of deeper principles that appear throughout physics. Looking at the vast body of experimental evidence for tunneling, from radioactive decay to scanning, tunneling microscopes, from Josephson junctions to flash memory, we see a phenomenon that has moved from impossible paradox to practical tool in less than a century. We've gone from puzzling over how alpha particles could escape atomic nuclear to engineering devices that depend on precise control of tunneling probabilities. This transformation represents one of the great success stories of 20th century physics, a demonstration of humanity's ability to understand and harness even the strangest aspects of nature. But perhaps what's most remarkable about the experimental study of tunneling is how it continues to surprise us. Just when we think we fully understand tunneling, new experiments reveal unexpected subtleties or new contexts where tunneling plays a crucial role. Recent experiments have shown tunneling in chemical reactions we didn't expect, in biological systems we thought were too warm and noisy for quantum effects in materials and conditions where classical physics should dominate. Each new discovery reminds us that the quantum world is richer and more pervasive than we imagined. As you lie there, surrounded by the quiet testimony of countless tunneling events happening in the atoms around you and within you, consider what this vast body of experimental evidence tells us. It tells us that nature really does allow particles to cross barriers they don't have energy to climb over. It tells us that this isn't rare or exceptional, but common and essential. It tells us that we can understand, predict, and control this seemingly impossible phenomenon with extraordinary precision. And it tells us that the universe is far stranger and more wonderful than our everyday experience would suggest. The experiments we've discussed tonight, from Gamow's explanation of alpha decay to modern attosecond spectroscopy, represent humanity's patient, careful investigation of nature's quantum secrets. Each experiment was a question posed to nature. Do particles really tunnel? How fast? Under what conditions? With what probability? And nature has answered, not with words, but with data, with measurements that confirm again and again that quantum tunneling is real, reliable, and essential to the workings of our universe. As we float deeper into contemplation of quantum tunneling, let us turn from the how to the why, from the mechanisms to the meaning, from the equations to the implications that ripple outward through our understanding of reality itself. What does it mean that particles can tunnel through barriers they don't have energy to cross? What does this tell us about the nature of the universe we inhabit, about the stars that shine above us, about the very atoms that compose our bodies? The answers, as we'll discover, touch everything from the birth of stars to the chemistry of life, from the stability of matter to the nature of possibility itself. Let's begin with the stars, those distant suns that have captivated humanity since we first looked up at the night sky. Every star is, at its heart, a vast nuclear fusion reactor, converting hydrogen into helium and releasing enormous amounts of energy in the process. But here's something that might surprise you. The temperature at the core of our Sun, about 15 million degrees Celsius, is actually not hot enough for hydrogen nuclei to overcome their electromagnetic repulsion and fuse together. If classical physics were the whole story, the Sun shouldn't shine, or at least not in the steady, reliable way it has for billions of years. The problem is that hydrogen nuclei, being protons, are positively charged, and like charges repel each other. As two protons approach each other, the repulsive force between them grows stronger, creating an energy barrier that prevents them from getting close enough for the strong nuclear force to take over and bind them together. At the temperature of the Sun's core, protons typically have only about 1 keV of kinetic energy, but they need about 1 MeV to overcome the electromagnetic barrier classically. That's 1,000 times more energy than they actually have. By all rights of classical physics, fusion in the Sun should be impossible. Yet the Sun shines, and it has been shining steadily for about 4.5 billion years. The resolution of this paradox lies in quantum tunneling. Even though the protons don't have enough energy to overcome the electromagnetic barrier, their quantum wave nature allows them to tunnel through it. The probability of any individual pair of protons tunneling close enough to fuse is incredibly tiny. But the Sun contains about 1057 protons, and they're constantly colliding with each other billions of times per second. Even with a tunneling probability of 1 in 10 to 28 per collision, fusion reactions occur frequently enough to power the Sun. Think about what this means. Every ray of sunlight that warms your face, every photon that drives photosynthesis in plants, every bit of solar energy that powers our climate and weather exists because particles in the sun's core are doing something that classical physics says is impossible. They're tunneling through barriers they can't climb over, fusing together and releasing the energy that makes life on Earth possible. Without quantum tunneling, the sun would be a slowly cooling ball of gas, and Earth would be a frozen, lifeless rock in space. But the role of tunneling in stars goes even deeper. The specific rate at which protons tunnel and fuse determines how fast a star burns through its nuclear fuel, and thus how long it lives. More massive stars have higher core temperatures, which increases both the classical collision rate and the tunneling probability, causing them to burn their fuel much faster and live shorter lives. Our Sun, a relatively modest star, can shine steadily for about 10 billion years thanks to the precise balance between its mass, temperature, and the quantum tunneling rates in its core. This long, stellar lifetime has given evolution enough time to produce complex life on Earth. The synthesis of heavier elements in stars also depends critically on tunneling. As stars age and exhaust their hydrogen fuel, they begin fusing helium into carbon, carbon into oxygen, and so on up the periodic table. Each of these fusion reactions requires nuclei to tunnel through electromagnetic barriers. The famous triple alpha process, where 3 helium nuclei come together to form carbon, is particularly dependent on tunneling and on a remarkable coincidence in nuclear energy levels that Fred Hoyle predicted must exist for carbon to be produced in stars. Without this coincidence and without tunneling, the universe would contain only hydrogen and helium, and the complex chemistry necessary for life would be impossible. When massive stars reach the end of their lives and explode as supernova, the extreme conditions allow rapid nucleosynthesis through a combination of neutron capture and beta decay. Many of these processes involve tunneling, either of neutrons through nuclear barriers or of electrons and neutrinos in beta decay. The gold in jewelry, the uranium in nuclear reactors, the iron in your blood, all of these elements heavier than iron were forged in the death throes of massive stars in processes that required quantum tunneling to proceed. But tunneling doesn't just shape the cosmos, it shapes the chemistry of life itself. In biological systems, enzymes catalyze chemical reactions by lowering activation energy barriers, but even with enzymatic assistance, many crucial reactions would proceed too slowly to sustain life if they relied solely on classical thermal activation. Instead, life has evolved to exploit quantum tunneling, particularly the tunneling of protons and electrons in enzymatic reactions. Consider the enzyme alcohol dehydrogenase, which helps break down alcohol in your liver. This enzyme catalyzes the transfer of a hydrogen atom from alcohol to a coenzyme molecule. Careful isotope effect studies, where regular hydrogen is replaced with deuterium or tritium, have shown that this transfer involves significant quantum tunneling. The lighter hydrogen nuclei tunnel more readily than the heavier isotopes, causing the reaction to proceed faster with regular hydrogen than with deuterium. This isotope effect is larger than can be explained by classical physics alone, providing clear evidence for tunneling. DNA polymerase, the enzyme that copies DNA during cell division, also appears to use proton tunneling. The enzyme must discriminate between correct and incorrect base pairs with extraordinary accuracy, making less than 1 error per billion bases copied. This accuracy is higher than can be explained by the energy differences between correct and incorrect base pairs at body temperature. Some researchers suggest that quantum tunneling of protons between base pairs might contribute to this remarkable fidelity, with incorrect pairs having different tunneling rates than correct ones. Even photosynthesis, the process by which plants convert sunlight into chemical energy, might involve quantum tunneling. In the reaction centers of photosynthetic complexes, electrons must move from donor to acceptor molecules across distances of several nanometers in times of picoseconds. The speed and efficiency of this electron transfer suggests that tunneling plays a crucial role. Some experiments have even found evidence for quantum coherence in photosynthetic complexes, where electrons exist in superposition states that allow them to explore multiple paths simultaneously, though this remains an active area of research and debate. The role of tunneling in biology extends to the very mechanisms of genetic mutation and evolution. DNA bases can exist in rare tautomeric forms where protons have shifted position, changing the base's hydrogen bonding pattern and potentially causing it to pair with the wrong partner during DNA replication. The transition between normal and tautomeric forms involves proton transfer that can occur through tunneling. While most such mutations are corrected by cellular repair mechanisms, some slip through and contribute to the genetic variation upon which natural selection acts. In this view, quantum tunneling is not just compatible with life, but is one of the engines driving evolutionary change. Moving from biology to technology, we find that our modern world is built on devices that exploit quantum tunneling. The flash memory that stores data in billions of smartphones, tablets, and computers worldwide depends on electrons tunneling through insulating barriers. Every time you save a photo, send a message, or download an app, you're relying on quantum tunneling to store that information. The transistors in modern computer processors are so small that tunneling through the gate oxide has become a major design consideration, limiting how small we can make classical transistors and driving the search for new quantum computing architectures. The scanning tunneling microscope has revolutionized our ability to see and manipulate matter at the atomic scale. This tool has enabled breakthroughs in nanotechnology, allowing scientists to build structures atom by atom, to study the electronic properties of individual molecules, and to observe quantum phenomena directly. The images produced by scanning tunneling microscopes have become iconic, showing us the atomic world in unprecedented detail and beauty. They've revealed the wave nature of electrons confined to quantum corrals, the atomic structure of graphene and other two-dimensional materials, and even the dance of individual molecules on surfaces. Josephson junctions, which exploit the tunneling of Cooper pairs between superconductors, have enabled some of the most precise measurements in physics. They're used in squids to detect the tiny magnetic fields produced by brain activity, helping doctors diagnose neurological conditions. They're used in quantum computers as qubits, the quantum bits that can exist in superposition states. They're used in voltage standards that define the volt to extraordinary precision. These applications show how tunneling, far from being just a theoretical curiosity, has become essential to cutting-edge technology and precision measurement. But beyond these practical applications, tunneling tells us something profound about the nature of reality itself. It tells us that the universe is not the deterministic clockwork mechanism that classical physics suggested. Instead, it's a realm of possibilities and probabilities, where the seemingly impossible can and does happen. Every tunneling event is a small violation of classical determinism, a moment where the universe could go one way or another and chooses based on probability rather than certainty. This probabilistic nature of quantum mechanics, exemplified by tunneling, has profound philosophical implications. If the universe is fundamentally probabilistic, if there's genuine randomness at its base, then the future is not completely determined by the present. There's room for novelty, for surprise, for genuine choice. Some philosophers and physicists have suggested that this quantum indeterminacy might be connected to free will, though this remains highly controversial and speculative. The existence of tunneling also tells us something about the nature of barriers and boundaries. In the classical world, barriers are absolute. You're either on one side or the other, and crossing requires a definite expenditure of energy. But quantum mechanics reveals that barriers are more subtle, more permeable than we thought. Every barrier is porous at the quantum level. Every wall has some transparency to quantum waves. This porosity of quantum barriers suggests that the universe is more interconnected, more fluid than classical physics indicated. Consider what this means for our understanding of possibility and impossibility. In classical physics, if you don't have enough energy to overcome a barrier, crossing it is simply impossible. End of story. But quantum mechanics says that impossible is too strong a word. Highly improbable is more accurate. Given enough particles and enough time, even the most improbable tunneling events will occur. This shifts our perspective from a universe of absolute limits to one of probabilistic boundaries, from hard impossibilities to soft improbabilities. This shift has practical implications for how we think about rare events and long-term stability. No atomic nucleus is absolutely stable. Even the most stable isotopes have some infinitesimally small probability of decay through tunneling. No data stored in flash memory is absolutely permanent. There's always some tiny probability of electrons tunneling out spontaneously. No barrier is absolutely impermeable. Given enough time, anything can tunnel through anything. Of course, for many practical purposes, these probabilities are so small that we can ignore them. The proton is thought to have a half-life of at least 1034 years, far longer than the age of the universe. But the fact that it's not infinite, that there's some probability of decay, represents a fundamental difference between the quantum and classical worldviews. Tunneling also illuminates the deep connection between the quantum and classical worlds. In our everyday experience, we don't see objects tunneling through walls because the probability decreases exponentially with the mass of the object. For anything much heavier than an atom, the tunneling probability is so vanishingly small that it would never happen, even if we waited for times far exceeding the age of the universe. This is why the classical world seems so solid and predictable, despite being built on quantum foundations. The classical world emerges from the quantum through the law of large numbers and the suppression of quantum effects for massive objects. Yet even in the macroscopic world, tunneling can have observable effects when amplified through chain reactions or sensitive dependencies. A single cosmic ray particle tunneling through a transistor in a computer could flip a bit, potentially causing a program to crash or produce incorrect results. A single radioactive decay in a smoke detector triggers an alarm that could save lives. A single mutation caused by proton tunneling in DNA could lead to cancer or, over evolutionary time, to new species. These examples show how quantum events can cascade up to influence the macroscopic world. The philosophical implications of tunneling extend to our understanding of scientific knowledge itself. The discovery and explanation of tunneling showed that our intuitions, evolved to help us survive in the macroscopic world, are not reliable guides to how nature works at its most fundamental level. We cannot trust our common sense when it comes to quantum phenomena. Instead, we must rely on mathematics and experimental evidence, even when they lead us to conclusions that seem absurd. This represents a profound shift in how we understand understanding itself, from intuition-based to evidence-based, from what seems reasonable to what the equations and experiments tell us. As you rest there, perhaps feeling your thoughts beginning to soften and merge like overlapping probability waves, consider what quantum tunneling tells us about our place in the universe. We are not separate from the quantum world, observing it from outside. We are part of it, made of it, sustained by it. The atoms in our bodies, the molecules that carry out the chemistry of life, the very processes of thought in our brains, all are governed by quantum mechanics, including tunneling. We are quantum beings living in a quantum universe, even if the classical approximation works well enough for most of our daily experience. This quantum nature of our existence connects us to the cosmos in profound ways. The carbon atoms in our DNA, the oxygen we breathe, the iron in our blood, all were forged in stars through fusion reactions that required quantum tunneling. The sun that powers all life on Earth shines because of tunneling in its core. The genetic variations that allowed evolution to produce the complexity of life arise in part from tunneling events in DNA. We are not just observers of quantum phenomena, we are products of them, manifestations of them, living examples of what quantum mechanics makes possible. The discovery and understanding of quantum tunneling also represents a triumph of human intellect and creativity. Faced with phenomena that completely contradicted everyday experience, physicists didn't retreat into denial or mysticism. They developed new mathematics, performed careful experiments, and followed the evidence wherever it led. The result was not just an explanation of puzzling observations, but a revolution in our understanding of reality itself. This success gives us hope that we can understand other mysteries that currently perplex us, from the nature of consciousness to the origin of the universe. We come back again and again to the same simple question that has guided our journey through the quantum realm tonight. Why can particles tunnel through walls they don't have energy to cross? Each time we return to this question, we see it with new eyes, understanding it more deeply, appreciating its implications more fully. Like a meditation mantra that reveals new meanings with repetition, this question has become our companion, our guide through the strange and beautiful landscape of quantum mechanics. Let us circle back once more, moving even more slowly now, letting the mystery settle into our bones like a deep, peaceful knowing. Perhaps this question has been here all along, waiting patiently through the ages for minds capable of asking it. For most of human history, the very idea would have seemed like nonsense, a contradiction in terms. Walls are walls, barriers are barriers. If you don't have enough energy to cross them, you don't cross them. This was not just common sense, but the foundation of survival itself. Our ancestors needed to know which cliffs they could climb and which they couldn't, which rivers they could cross and which would sweep them away. The classical physics of everyday experience, where energy requirements are absolute and barriers are impermeable, kept them alive. But perhaps in every barrier humanity has ever encountered, there has been a hint of this deeper story. Perhaps in every wall that seemed absolute, every mountain that seemed unclimbable, every impossibility that seemed final, there was a whisper of quantum possibility, too faint for us to hear until we developed the tools and concepts to listen. The universe has always been quantum mechanical. Particles have always been tunneling. We just didn't know it until the 20th century, when careful observations and brilliant insights revealed what had been happening all along, hidden in plain sight. As you lie there, breathing slowly, feeling perhaps the weight of your body settling into rest, you are yourself a collection of particles, roughly 1028 atoms arranged in patterns of extraordinary complexity. Each of these atoms is a quantum system, its electrons occupying probability clouds around the nucleus, its very stability dependent on quantum mechanics. And within these atoms, constantly, quietly, particles are exploring the boundaries of their quantum walls. Most stay within their classical limits, but some, always some, venture into the classically forbidden regions, tunneling through barriers that classical physics says they cannot cross. You are, in a very real sense, made of waves as much as particles. The electrons in your atoms don't orbit the nucleus like tiny planets around a sun. Instead, they exist as standing waves, probability patterns that give them a chance of being found at different locations. These electron waves overlap and interfere with each other, creating the complex molecular orbitals that allow atoms to bond together into molecules. The very chemistry of your body, the proteins that catalyze reactions, the DNA that stores genetic information, the lipids that form cell membranes, all depend on the wave nature of electrons. And because you are made of waves, you are made of entities that can tunnel. The enzymes in your cells use tunneling to catalyze reactions that would otherwise proceed too slowly to sustain life. The mitochondria that power your cells depend on electron tunneling in their respiratory chains. Even the neurons in your brain, as they fire and communicate with each other, involve quantum processes that include tunneling of ions through channel proteins. You're not just an observer of quantum tunneling, you're a living embodiment of it, a biological system that has evolved to exploit quantum mechanics for the processes of life. Let's revisit what we've learned, but more slowly this time, letting each insight settle like sediment in still water. We began with the classical picture, particles as tiny solid spheres, barriers as walls that require energy to cross. This picture works well at the scale of everyday experience, and our intuitions are built around it. But as we looked closer, at the scale of atoms and subatomic particles, this picture began to dissolve. Particles revealed themselves to be waves as well, spreading out through space, existing in superpositions of different states until measurement collapsed them into definite outcomes. When these particle waves encounter barriers, they don't stop abruptly but penetrate into them, their amplitude decreasing exponentially with distance. If the barrier is thin enough, some amplitude emerges on the far side, giving a probability of finding the particle there, even though it never had enough energy to cross classically. This is tunneling. Not a violation of physical laws, but a consequence of them, emerging naturally from the wave nature of matter and the probabilistic nature of quantum mechanics. We explored the experimental evidence, from radioactive decay to scanning tunneling microscopes, from Josephson junctions to flash memory. Each experiment confirmed that tunneling is real, measurable, and predictable. We can calculate tunneling probabilities with extraordinary precision, and nature always agrees with our calculations. The same equations that describe electron tunneling in a laboratory device also describe proton tunneling in the sun's core, alpha particle tunneling in radioactive decay, and countless other quantum processes throughout the universe. We discovered that tunneling shapes the cosmos, enabling the fusion reactions that power stars and create the elements. Without tunneling, the universe would be dark and cold, containing only hydrogen and helium, with no possibility for the complex chemistry needed for life. We found that tunneling shapes biology, enabling enzymatic reactions, contributing to genetic mutations, and possibly playing roles in photosynthesis and other crucial life processes. We saw how technology has harnessed tunneling, from the flash memory that stores our digital lives, to the scanning, tunneling microscopes that let us see and manipulate individual atoms. And we contemplated the deeper implications, what tunneling tells us about the nature of reality, about possibility and impossibility, about the relationship between the quantum and classical worlds. We saw that the universe is not the rigid, deterministic machine that classical physics suggested, but something more fluid, more probabilistic, more open to possibility. Every tunneling event is a small window into this deeper nature of reality, a reminder that the impossible happens regularly, quietly, everywhere. Now, as we circle back to our central question once more, perhaps we can see it not as a paradox to be resolved, but as a koan to be contemplated, a mystery that opens our minds to deeper understanding. Why can particles tunnel through walls they don't have energy to cross? Because particles are not what we thought they were. Walls are not what we thought they were. Energy is not what we thought it was. Even the concept of crossing needs to be reconsidered in the quantum realm. A particle approaching a barrier doesn't simply bounce off or pass through. Its wave function explores all possibilities simultaneously. Part of it reflects. Part of it enters the barrier and decays exponentially. And if the barrier is thin enough, part emerges on the other side. The particle doesn't take a definite path through the barrier. It exists in a superposition of all possible paths until measurement forces it to be found on one side or the other. In some interpretations of quantum mechanics, the particle takes all paths simultaneously. In others, it follows a guide wave that leads it through the barrier. In still others, the universe splits into branches where the particle tunneled and didn't tunnel. But regardless of interpretation, the mathematics is clear and unambiguous. We can calculate exactly how likely a particle is to tunnel through any given barrier, and experiments confirm these calculations with remarkable precision. The mystery is not in the mathematics, but in what the mathematics means, in how we should understand what's really happening when a particle tunnels. This gap between mathematical precision and conceptual understanding is one of the defining features of quantum mechanics. We can predict perfectly without fully understanding what we're predicting. Perhaps this is appropriate. Perhaps a universe strange enough to allow particles to tunnel through walls they can't climb over should also be strange enough to elude our complete conceptual grasp. Perhaps the mystery is not a problem to be solved, but a feature of reality to be appreciated. The universe is under no obligation to be fully comprehensible to minds that evolved to navigate the African savanna. That we can understand it as well as we do, that we can predict quantum phenomena with such precision even if we can't fully visualize them, is itself remarkable. As you rest there, letting these ideas wash over you like gentle waves, imagine yourself shrinking down to the quantum scale. Your solid form dissolves into probability clouds. The barriers around you become not walls but regions of decreasing probability. You exist not at a single point, but spread out through space, your wave function extending even into classically forbidden regions. From this perspective, tunneling is not strange but natural, not exceptional but inevitable. It would be stranger if particles couldn't tunnel, if the universe were as rigid and absolute as classical physics suggested. Now imagine zooming back out to the everyday scale, watching as quantum uncertainties average out to give the apparently solid, predictable world of daily experience. The chair you're resting on seems solid because the quantum uncertainties of its countless atoms average out to give a stable structure. The walls around you seem impermeable because the probability of macroscopic objects tunneling through them is so vanishingly small that it would never happen even if you waited for times far exceeding the age of the universe. The classical world emerges from the quantum, not as a different reality but as a limiting case. What happens when quantum systems become large and numerous enough that their individual uncertainties cancel out? Yet even in this classical-seeming world, quantum tunneling continues its quiet work. In the electronic devices around you, electrons tunnel through carefully engineered barriers. In your body, enzymes use tunneling to catalyze the reactions of life. In the rocks beneath you, radioactive nuclei decay through tunneling. In the sun above, protons tunnel through electromagnetic barriers to fuse and release the energy that ultimately powers all life on Earth. The classical world is shot through with quantum phenomena, dependent on them, impossible without them. We come back again and again to find new meaning in our question. Why can particles tunnel through walls they don't have energy to cross? Because the universe is more generous with possibility than classical physics suggested. because nature has built flexibility into its most fundamental laws, because particles are waves and waves don't stop abruptly at boundaries, because the quantum world is richer, stranger, and more wonderful than our everyday experience would lead us to expect, because this is how the universe actually works, whether we understand it fully or not. Perhaps in every barrier you've encountered in life, there has been a hint of this deeper truth. The obstacles that seemed insurmountable, the walls that seemed impermeable, the impossibilities that seemed absolute. Perhaps they all contained within them some small probability of passage, some quantum possibility of tunneling through. Not in the literal sense of macroscopic quantum tunneling, which remains vanishingly improbable for everyday objects, but in the metaphorical sense that the universe is less rigid, less absolute, more open to possibility than it might appear. This is not to say that anything is possible or that we can ignore the laws of physics through wishful thinking. Tunneling probabilities are governed by strict mathematical laws. Most particles don't tunnel, most barriers remain barriers. The vast majority of quantum events follow classical-like paths. But the existence of tunneling, the fact that it happens at all, tells us something important about the nature of reality. It tells us that the universe has soft edges, that absolute prohibitions are rarer than we might think, that nature often finds ways to do what seems impossible. As we continue to circle our central question, notice how it has transformed from a puzzle to be solved into a doorway to deeper understanding. The question itself has become a kind of meditation object, something we can return to again and again, always finding new facets, new implications, new connections to other aspects of physics and philosophy. This is the nature of deep questions in science. They don't just have answers, but open up entire landscapes of investigation and wonder. Maybe, in every barrier you've met in life, there has been a hint of this deeper story. Not that you could literally quantum tunnel through physical walls. The probability of that remains absurdly, impossibly small for anything larger than subatomic particles, but rather that the universe itself is less rigid than it appears, that what seems impossible from one perspective might be inevitable from another, that patience and probability can sometimes accomplish what force and energy cannot. The mathematics of tunneling tells us that the probability depends exponentially on the barrier width. Make a barrier just slightly thinner, and the tunneling probability can increase dramatically. Perhaps there's a life lesson hidden in this mathematical truth. Sometimes the barriers we face are thinner than they appear. Sometimes a small change in conditions can dramatically increase the probability of crossing. Sometimes what matters is not having more energy, but finding where the barrier is thinnest. We return to our question with a sense of peace now, no longer troubled by its apparent contradiction. Particles can tunnel through walls they don't have energy to cross because that's the kind of universe we live in, one where waves and particles are two faces of the same reality, where probability and possibility are woven into the fabric of existence, where the impossible happens quietly, constantly, beautifully. This is not a bug in the universe's operating system, but a feature, one that makes possible the stars, the elements, life itself. Consider how your understanding has shifted since we began this journey. At first, tunneling might have seemed like an exotic anomaly, a strange exception to the normal rules. But now perhaps you can see it as fundamental, essential, woven into the very nature of reality. The universe is not classical mechanics with quantum corrections added on top. It's quantum mechanical through and through, with classical mechanics emerging as an approximation that works well for large, warm, noisy systems like the ones we encounter in daily life. This shift in perspective, from seeing quantum mechanics as strange to seeing it as fundamental, represents a profound change in how we understand reality. We're not living in a classical world where quantum effects occasionally intrude. We're living in a quantum world where classical behavior emerges under certain conditions. Tunneling is not the exception but part of the rule, not an anomaly but an aspect of how particles naturally behave when they're being particles, which is to say, when they're also being waves. As your thoughts continue to soften and drift, becoming more wave-like themselves perhaps, spreading out through possibilities rather than following single tracks, you might feel yourself becoming more comfortable with the mystery of tunneling, not because it has been solved, in many ways it remains as mysterious as ever, but because you've spent time with it, turned it over in your mind, seen it from different angles. Familiarity with mystery doesn't eliminate the mystery, but can transform our relationship with it, from confusion to wonder, from frustration to appreciation. The question we've been contemplating, why can particles tunnel through walls they don't have energy to cross, has become like a familiar friend, one whose depths we're still discovering. Each time we return to it, we see something new. The experimental evidence that confirms it really happens. The cosmic implications for stars and elements. The biological implications for enzymes and evolution. The technological applications in devices we use every day. The philosophical implications for determinism and possibility. Layer upon layer of meaning, all emerging from this simple quantum phenomenon. And perhaps this is how we should approach all the deep mysteries of existence. Not as problems to be quickly solved and filed away, but as koans to live with, to return to contemplate from different angles as we ourselves grow and change. The mystery of consciousness, the origin of the universe, the nature of time, these too might be questions we circle back to throughout our lives, each return bringing new insights, new connections, new appreciation for the depth of the mystery. And now, as we drift even deeper into the quantum landscape, let us explore some of the more subtle aspects of tunneling that we've only touched upon lightly. Like examining a beautiful crystal from different angles, each new perspective reveals different colors, different patterns, different ways the light plays through its structure. The phenomenon of quantum tunneling, simple as it might seem in its basic concept, contains within it layers upon layers of nuance and complexity that scientists continue to discover and explore even today. Consider first the shape of the barrier itself. In our discussion so far, we've mostly imagined simple rectangular barriers, walls that rise abruptly to a certain height and then drop just as abruptly on the other side. But real barriers in nature are rarely so simple. They might be rounded, sloping gradually up and then down again. They might have multiple peaks, like a mountain range that particles must traverse. They might even have dips and valleys within them, creating what physicists call resonant structures. Each of these different barrier shapes affects the tunneling probability in its own unique way, creating a rich tapestry of quantum behavior. When a barrier is rounded rather than rectangular, the tunneling probability generally increases. This is because the particle spends less distance at the maximum barrier height. Think of it like the difference between tunneling through a steep mountain versus a gently sloping hill. Even if both reach the same maximum height, the hill provides more opportunities for the particle's wave function to maintain some amplitude as it penetrates through. This is why nuclear physicists often model the nuclear potential as a rounded barrier when calculating alpha decay rates. The actual electromagnetic repulsion between an alpha particle and the remaining nucleus doesn't create a sharp wall, but rather a smooth potential that decreases with distance. But perhaps even more fascinating is what happens when barriers have special structures that create resonances. Imagine a barrier with a dip in the middle, creating essentially two thin barriers separated by a small well. At certain specific energies, a particle's wave can resonate within this well, bouncing back and forth between the two barriers. When this resonance occurs, the tunneling probability can increase dramatically, sometimes approaching 100%. It's as if the particle has found a secret frequency that makes the barrier temporarily transparent. This resonant tunneling is not just a theoretical curiosity, but has practical applications in modern electronics. Resonant tunneling diodes use carefully engineered double barrier structures to create devices with unique electrical properties. At specific voltages corresponding to resonant energies, the current through the device increases sharply, creating negative resistance regions where increasing voltage actually decreases current. These devices can switch extremely quickly and are used in high-frequency oscillators and some types of quantum cascade lasers. The width of the barrier remains perhaps the most critical factor in determining tunneling probability. The exponential dependence on width means that even small changes can have enormous effects. A barrier that's 1 nanometer thick might allow 1 in 1,000 particles to tunnel through. Make it 2 nanometers thick, and perhaps only 1 in a million makes it through. 3 nanometers, and we're down to 1 in a billion. This extreme sensitivity to barrier width is both a challenge and an opportunity in designing quantum devices. In flash memory, for instance, the insulating barrier that electrons must tunnel through is typically just 8 to 10 nanometers thick. This thickness is chosen very carefully. Too thin, and electrons tunnel out spontaneously, causing data loss. Too thick, and the high voltages needed to force electrons through during writing would damage the device. Modern flash memory can retain data for years because the barrier is thick enough that spontaneous tunneling is extremely rare, yet thin enough that controlled tunneling is still possible with reasonable voltages. The mass of the tunneling particle plays a crucial role that we can now appreciate more fully. The tunneling probability decreases exponentially with the square root of the particle's mass. This means that electrons, being about 2,000 times lighter than protons, tunnel much more readily. This mass dependence explains why quantum effects are generally more noticeable for electrons than for atomic nuclei, and why molecular tunneling, involving entire atoms or groups of atoms, is extremely rare except at very low temperatures where thermal fluctuations don't mask the quantum effects. Yet even heavy particles can tunnel when conditions are right. In the Sun's core, it's not just individual protons that must tunnel, but pairs of protons that must come together to form deuterium. The effective mass for this process is twice the proton mass, making tunneling even less likely. Yet it happens billions of times per second, because of the enormous number of collisions occurring in the Sun's dense, hot core. Each fusion event that lights the stars is a testament to the persistence of quantum probability. Given enough attempts, even the most unlikely tunneling events will occur. Temperature plays a subtle but important role in tunneling, while tunneling itself is not a thermal process. Particles don't need thermal energy to tunnel. Temperature affects the number of particles that reach the barrier and their energy distribution. At higher temperatures, more particles have energies closer to the barrier height, making tunneling more likely. This is why fusion reactions in stars are so sensitive to temperature. A small increase in core temperature can dramatically increase the fusion rate, not just because particles collide more frequently, but because they tunnel more readily when they have higher energies. In the ultra-cold world near absolute zero, different aspects of tunneling become apparent. When atoms are cooled to nanokelvin temperatures in laboratory experiments, their quantum wave nature becomes dominant. Entire atoms can tunnel between sites in optical lattices, arrays of potential wells created by interfering laser beams. Scientists can watch in real time as atoms tunnel back and forth, creating quantum mechanical oscillations that would be impossible in the classical world. These experiments provide some of the cleanest, most controlled observations of quantum tunneling, free from the thermal noise that usually obscures quantum effects. One particularly beautiful experiment involves creating what's called a Bose-Einstein condensate, a state of matter where thousands or millions of atoms all occupy the same quantum state. When such a condensate encounters a barrier, the entire condensate can tunnel through coherently, with all atoms maintaining their quantum correlation. This is macroscopic quantum tunneling, where a relatively large object containing many atoms behaves as a single quantum entity. While the condensate is still microscopic by everyday standards, it's enormous compared to individual particles, demonstrating that quantum tunneling is not limited to single particles, but can involve collective quantum states. The phenomenon of co-tunneling adds another layer of complexity to our understanding. Sometimes, two or more particles can tunnel simultaneously in a correlated way, even when neither could tunnel alone. This can happen in quantum dots, tiny islands of semiconductor material that can trap individual electrons. When the energy cost of adding a single electron to the dot is too high, it might still be possible for one electron to tunnel in while another tunnels out simultaneously, keeping the total energy constant. This co-tunneling process is crucial for understanding electronic transport in many nanoscale devices. In superconductors, we encounter perhaps the most remarkable form of tunneling, the Josephson effect. Here, it's not individual electrons that tunnel, but Cooper pairs, bound, pairs of electrons that carry current without resistance in superconductors. When two superconductors are separated by a thin insulating barrier, Cooper pairs can tunnel through, creating a Josephson junction. What makes this special is that the pairs maintain their quantum phase coherence while tunneling, leading to remarkable effects like the ability to generate extremely precise microwave radiation or detect incredibly small magnetic fields. The AC Josephson effect, where a constant voltage across the junction produces an alternating current with a frequency precisely proportional to the voltage, has become the basis for the most accurate voltage standards in metrology. The frequency of the AC current is given by 2 EVH, where E is the electron charge, V is the voltage, and H is Planck's constant. This provides a direct link between electrical measurements and fundamental constants of nature, allowing voltage to be measured with unprecedented precision. It's a beautiful example of how quantum tunneling connects the microscopic quantum world to macroscopic electrical measurements. Recent experiments have pushed our ability to observe and control tunneling to new extremes. Using ultrafast laser pulses lasting just attoseconds, billionths of a billionth of a second, scientists can now observe tunneling in real time, or at least as close to real time as the uncertainty principle allows. These experiments have revealed that tunneling is not instantaneous, as was once thought, but takes a finite, though extremely short, time. The exact nature of this tunneling time remains controversial, with different experiments and theoretical approaches giving different answers. One approach uses what's called an attaclock, where a circularly polarized laser field ionizes atoms, and the angular distribution of the emitted electrons provides information about when they tunneled out. These experiments suggest that tunneling takes a few attoseconds, though the interpretation of these results is still debated. Another approach uses atoms as stopwatches, looking at how the internal state of an atom changes during tunneling to infer how long the process takes. These experiments sometimes suggest even shorter tunneling times, possibly approaching zero for very thin barriers. The question of tunneling time touches on deep issues in quantum mechanics. What does it mean for a particle to spend time in a classically forbidden region, where it supposedly doesn't have enough energy to exist? How can we measure the duration of a process that we cannot observe directly without destroying it? These questions remain at the forefront of quantum physics research, reminding us that even well-understood phenomena like tunneling still harbor mysteries. In materials science, tunneling plays crucial roles that we're only beginning to fully appreciate. In scanning tunneling spectroscopy, the voltage-dependent tunneling current provides information about the electronic density of states in materials, revealing details about their electronic structure that would be impossible to obtain otherwise. This technique has been instrumental in studying exotic materials like graphene, topological insulators, and high-temperature superconductors. Spin-polarized tunneling adds yet another dimension to the phenomenon. When magnetic materials are involved, the tunneling probability can depend on the spin orientation of the electrons. This spin-dependent tunneling is the basis for tunnel magnetoresistance, an effect used in modern hard drive read heads and magnetic RAM. By controlling the relative magnetization of two magnetic layers separated by a tunnel barrier, we can control the electrical resistance of the device, allowing information to be stored and read magnetically. The field of molecular electronics explores tunneling through individual molecules. When a molecule is placed between two electrodes, electrons must tunnel through the molecule to create a current. The tunneling probability depends on the molecule's electronic structure, its conformation, and even its vibrational states. This opens the possibility of creating electronic devices from individual molecules, potentially allowing electronics to be scaled down far beyond what's possible with conventional silicon technology. Some researchers have even demonstrated single-molecule switches and transistors, though many challenges remain before these can be practically implemented. Inelastic tunneling adds another layer of richness to the phenomenon. Sometimes, when a particle tunnels through a barrier, it can exchange energy with the barrier material, exciting vibrations or other excitations. This inelastic tunneling spectroscopy provides information about the vibrational modes of molecules and the phonon spectra of materials. In scanning tunneling microscopy, inelastic tunneling can reveal not just where atoms are, but what types of bonds they form and how they vibrate. The role of the environment in tunneling processes has become increasingly important as we push toward quantum technologies. Real quantum systems are never perfectly isolated. They're always interacting with their surroundings to some degree. These interactions can suppress tunneling through decoherence, where the quantum superposition necessary for tunneling is destroyed by environmental disturbance. Understanding and controlling decoherence is crucial for quantum computers, where we need to maintain quantum coherence long enough to perform calculations. But the environment doesn't always suppress tunneling. In some cases, it can enhance it through what's called environment-assisted tunneling. Fluctuations in the environment can temporarily lower the effective barrier height, making tunneling more likely. This effect is thought to be important in biological systems, where the warm, wet, noisy environment of living cells might actually help rather than hinder certain quantum processes. Some researchers have suggested that evolution has learned to exploit environment-assisted tunneling to enhance the efficiency of enzymatic reactions. The phenomenon of dynamical tunneling extends the concept beyond simple energy barriers. In classical mechanics, different regions of phase space, the space of all possible positions and momenta, can be separated by barriers that prevent classical trajectories from moving between them, but quantum mechanically, wave functions can tunnel between these regions, even when there's no classical path connecting them. This dynamical tunneling has been observed in systems ranging from molecules to ultra-cold atoms, showing that the concept of tunneling is even more general than just penetrating through energy barriers. As we explore these subtle aspects of tunneling, we see that what seemed like a simple phenomenon, particles crossing barriers they shouldn't be able to cross, actually encompasses a vast range of quantum behaviors. Each new experiment, each new theoretical insight reveals new facets of tunneling, new ways it manifests in nature, new applications we can exploit. The quantum landscape is rich with possibilities, and tunneling is our gateway to exploring them. The study of tunneling in many body systems, where multiple particles interact with each other while tunneling, has revealed even more complexity. In strongly correlated electron systems, the tunneling of one electron can be influenced by the positions and states of all the others, leading to exotic phenomena like the fractional quantum Hall effect. In ultra-cold atomic gases, the interplay between tunneling and interactions can lead to quantum phase transitions between different states of matter, such as the transition from a superfluid to a Mott insulator. These many-body tunneling effects are not just of academic interest. They're relevant to understanding high-temperature superconductors, materials that could revolutionize technology if we could understand and control them better. They're important for designing quantum simulators, devices that use controllable quantum systems to model other quantum systems that are too complex to simulate on classical computers. And they might even be relevant to understanding some biological processes where multiple electrons or protons might tunnel in coordinated ways. The connection between tunneling and quantum information has opened up entirely new perspectives on the phenomenon. In quantum computing, tunneling can be both a resource and a challenge. Quantum annealing computers deliberately use tunneling to find the global minimum of complex optimization problems, allowing the system to tunnel through barriers in the energy landscape rather than having to climb over them thermally. But unwanted tunneling can also cause errors in quantum computers, allowing qubits to leak out of their intended states. Quantum tunneling also plays a role in quantum cryptography, where the security of communication relies on the fundamental laws of quantum mechanics. Any attempt to intercept quantum encrypted information necessarily involves measuring quantum states, which disturbs them in detectable ways. The possibility of particles tunneling between different paths in a quantum communication system adds another layer of security, making it even harder for an eavesdropper to intercept information without being detected. As you rest there, perhaps feeling your awareness softening like a wave function spreading through space, consider how these subtle details of tunneling paint a picture of a universe that is far more intricate and interconnected than we might have imagined. Every barrier is not just a simple wall, but a complex quantum object with its own structure and dynamics. Every tunneling event is influenced by the particle's mass, energy, and spin, by the barrier's shape and composition, by the temperature and environment, by the presence of other particles and fields. Yet despite this complexity, or perhaps because of it, tunneling remains a reliable, predictable phenomenon that we can understand, calculate, and exploit. The same quantum mechanical principles that govern tunneling in radioactive nuclei also govern tunneling in electronic devices, in chemical reactions, in biological systems. This universality, this applicability across such vast scales and diverse contexts, speaks to the fundamental nature of tunneling as a basic feature of quantum reality. Now, as we float in this space between waking and sleeping, between the classical and quantum worlds, let us turn our attention to something more intimate, more personal. What does quantum tunneling mean for us as human beings? Not just as collections of atoms governed by quantum mechanics, but as conscious entities trying to understand our place in the universe, as beings who face our own barriers and seek our own passages through seemingly impossible situations. We are, each of us, approximately 7 quarks, 10 and 27 atoms, arranged in patterns of extraordinary complexity and beauty. These atoms, mostly hydrogen, carbon, nitrogen, and oxygen, with traces of other elements, are held together by electromagnetic forces, arranged into molecules by the sharing and exchanging of electrons. And in every one of these atoms, in every chemical bond, in every biological process that keeps us alive and aware, quantum mechanics is at work. We are not observers of the quantum world standing somehow outside it. We are manifestations of it, expressions of it, living examples of what quantum mechanics makes possible. Consider your breath, the gentle rhythm of air flowing in and out of your lungs as you rest there. With each inhalation, oxygen molecules enter your bloodstream, binding to hemoglobin proteins in your red blood cells. This binding process involves electrons moving between iron atoms and oxygen molecules, a transfer that happens partly through quantum tunneling. The efficiency with which hemoglobin captures and releases oxygen, so perfectly tuned to the needs of your body, depends on quantum mechanical effects that classical chemistry cannot fully explain. In your cells, in the mitochondria that are sometimes called the powerhouses of life, electron transport chains carry out the fundamental energy conversions that keep you alive. Electrons move between protein complexes, tunneling across gaps that would be insurmountable barriers in a classical world. The efficiency of these electron transfers, the speed at which they occur, the specificity with which electrons find their proper paths, all depend on quantum tunneling. Without it, the chemistry of life would grind to a halt, or more accurately, would never have begun in the first place. Even the thoughts you're having right now, the gentle flow of awareness as you listen to these words, might involve quantum processes. While the role of quantum mechanics in consciousness remains highly speculative and controversial, we know that the brain's neurons communicate through the movement of ions across cell membranes, and some of this movement involves quantum tunneling through protein channels. The neurotransmitters that carry signals between neurons must bind to receptor proteins, a process that involves electron rearrangements that can include tunneling. Whether these quantum effects are merely part of the brain's classical information processing, or whether they play a more fundamental role in consciousness itself, remains an open and fascinating question. But let's think beyond the physical and consider what tunneling might mean metaphorically for human experience. Throughout our lives, we encounter barriers of many kinds. Some are physical, like mountains to climb or distances to cross. Others are psychological, like fears to overcome or habits to change. Still others are social, economic, or creative, the barriers between where we are and where we want to be, between who we are and who we might become. While we cannot literally quantum tunnel through these macroscopic barriers, perhaps there's something to learn from the way particles navigate the quantum world. The first lesson might be about the nature of impossibility itself. Classical physics deals in absolutes. Either you have enough energy to cross a barrier or you don't. If you don't, crossing is impossible, end of story. But quantum mechanics reveals a universe where impossible is too strong a word. Highly improbable is more accurate. Even when the probability is vanishingly small, it's not zero. The universe maintains a kind of fundamental openness, a refusal to completely close off possibilities. Perhaps we too should be careful about declaring things impossible. Perhaps what seems impossible is merely highly improbable, waiting for the right conditions, the right approach, the right moment. The second lesson might be about persistence and probability. A single particle approaching a barrier has a very small chance of tunneling through, but send enough particles, or have one particle try enough times, and eventually tunneling will occur. The sun shines because trillions upon trillions of protons attempt to tunnel every second, and even though the vast majority fail, enough succeed to sustain fusion. Perhaps there's wisdom in this for human endeavours. Sometimes what matters is not having overwhelming force or energy, but having patience and persistence, trying enough times that even small probabilities eventually yield success. The third lesson might be about the importance of reducing barrier width, rather than trying to increase our energy to climb over barriers. In quantum tunneling, making a barrier even slightly thinner can dramatically increase the tunneling probability, much more than giving particles more energy would. Perhaps when we face barriers in life, we should look for ways to make them thinner rather than always trying to build up more energy to overcome them. Can the barrier be divided into smaller pieces? Can we find where it's thinnest? Can we change conditions to effectively reduce its width? Think about human creativity and innovation. How often have breakthrough ideas seemed to come from nowhere, as if they tunneled through the barriers of conventional thinking. The history of science is full of such moments. When Max Planck introduced the idea of quantized energy to explain black-body radiation, he was essentially tunneling through the conceptual barrier that energy must be continuous. When Einstein proposed that space and time were relative, he tunneled through the barrier of absolute space and time that had seemed unquestionable. These weren't logical deductions from existing knowledge, but quantum leaps, if you will, to entirely new ways of understanding reality. Human curiosity itself might be seen as a kind of tunneling phenomenon. We are constantly probing the barriers of our knowledge, looking for ways through to new understanding. Sometimes we build up enough intellectual energy to climb over these barriers through careful, systematic study. But sometimes, understanding comes through a different route, a sudden insight that seems to tunnel through the barrier without following the expected path. The aha moment when a difficult concept suddenly makes sense, when disparate pieces of knowledge suddenly connect, when a solution to a problem appears as if from nowhere. These feel very much like conceptual tunneling events. Consider how we learn and grow as individuals. Personal development often involves overcoming internal barriers, limiting beliefs, fears, old patterns of behavior that no longer serve us. The classical approach would be to build up enough willpower or motivation to overcome these barriers by force. But perhaps there's a quantum approach too, finding ways to reduce the effective height or width of these barriers, or finding resonant conditions where passage becomes suddenly easier. A supportive environment, the right teacher or mentor, a moment of inspiration, these might serve as the quantum conditions that make personal tunneling possible. The role of observation in quantum tunneling also has interesting parallels in human experience. In quantum mechanics, the act of observation collapses the wave function, forcing the particle to be definitely on one side of the barrier or the other. We cannot observe the tunneling process itself without disrupting it. Similarly, sometimes the most profound changes in human life happen when we're not directly observing or forcing them. The watched pot that never boils, the creative solution that comes when we stop actively thinking about the problem, the personal growth that happens gradually and unconsciously. These suggest that some human processes, like quantum tunneling, proceed best when not under direct observation. Our relationship with time also echoes something of the quantum tunneling experience. In classical physics, crossing a barrier takes a definite amount of time proportional to the distance and speed. But quantum tunneling time remains mysterious and controversial. Some experiments suggest it's nearly instantaneous, while others indicate finite but very short durations. In human experience too, the most significant transitions in our lives sometimes seem to happen outside of normal time. A moment of profound realization can change everything instantly, even though the preparation for that moment might have taken years. A barrier that seemed insurmountable for decades might suddenly become irrelevant in a moment of change perspective. The collective aspects of human endeavor also mirror something we see in quantum systems. Just as Bose-Einstein condensates can tunnel coherently as a single quantum entity, human societies sometimes make collective transitions that would be impossible for individuals. Social movements, paradigm shifts in science, cultural revolutions, these often involve entire communities tunneling through barriers of tradition, prejudice, or established thinking. The civil rights movement, the acceptance of quantum mechanics itself, the digital revolution, each involved collective tunneling through barriers that had seemed permanent. What does it mean that our minds, products of quantum processes in the atoms of our brains, can contemplate quantum mechanics itself? We are the universe becoming aware of its own quantum nature, using quantum tunneling in our neurons to think about quantum tunneling in the abstract. This strange loop, this self-reference suggests something profound about consciousness and its relationship to the physical world. We are not separate from the quantum phenomena we study, but examples of it, using quantum processes to understand quantum processes. The development of quantum mechanics itself required humanity to tunnel through enormous conceptual barriers. For centuries, physicists had built up a beautiful, coherent picture of the world based on classical mechanics. It explained so much, from planetary orbits to steam engines, from projectile motion to electromagnetic waves. To accept quantum mechanics required tunneling through the barrier of this established worldview, accepting ideas that seemed to contradict common sense and classical logic. That humanity managed this transition, that we could discover and accept a truth so foreign to our evolved intuitions, speaks to our remarkable capacity for intellectual tunneling. Today, As we stand on the brink of the quantum technology revolution, we're preparing to tunnel through another barrier. From a world where quantum mechanics is mostly important for understanding nature, to one where we actively harness quantum phenomena for computation, communication, and sensing. Quantum computers promise to tunnel through computational barriers that classical computers could never overcome. Quantum sensors will detect signals too faint for classical measurement. Quantum communication will provide security guaranteed by the laws of physics themselves. We are collectively tunneling into a quantum future. But perhaps the most profound human aspect of quantum tunneling is how it changes our relationship with mystery itself. Classical physics promised, at least in principle, complete understanding and prediction. If we could know the position and velocity of every particle in the universe, Laplace's demon could calculate the entire future and past. Quantum mechanics, with phenomena like tunneling, reveals a universe that is fundamentally probabilistic, where the future is not completely determined by the present, where mystery is not just a result of our ignorance, but a fundamental feature of reality. This permanent presence of mystery might seem unsettling at first. We like certainty, predictability, the feeling that the universe is ultimately comprehensible. But perhaps there's something liberating about living in a universe where mystery is fundamental, where the impossible occasionally happens, where there's always room for surprise. It means the future is not a fixed destination we're helplessly approaching, but a landscape of possibilities being constantly explored and decided. Every quantum tunneling event is a tiny choice point where the universe could go one way or another, and we are part of this ongoing creative process. As conscious beings in a quantum universe, we occupy a unique position. We're large enough that quantum effects usually average out in our bodies, giving us the stability needed for complex structures like brains. Yet we're made of quantum particles, dependent on quantum processes, products of quantum evolution. We exist at the sweet spot where classical and quantum meet, able to experience the predictable world of everyday life, while also being able to discover and appreciate the quantum foundation beneath it. Our ability to understand quantum tunneling, to measure it, predict it, and use it, represents a kind of intellectual tunneling through the barrier between the classical world of our experience and the quantum world of fundamental reality. Every equation we write describing tunneling, every experiment we perform to measure it, every device we build that exploits it, is a connection between these two realms. We are the universe's way of understanding itself, including its most mysterious and counterintuitive aspects. The questions that quantum tunneling raises, about determinism and free will, about the nature of reality, about the role of consciousness in physics, are not just scientific questions, but deeply human ones. They touch on our most fundamental concerns about who we are, why we're here, and what our place is in the cosmic order. That these questions arise from studying something as seemingly simple as particles crossing barriers they shouldn't be able to cross shows how deeply mystery and meaning are woven into the fabric of reality. And now, as we approach the end of our journey through the quantum realm, let the pace of our exploration slow even further, like a river approaching a calm lake, like thoughts beginning to dissolve into the peaceful darkness of approaching sleep. We have travelled far together tonight, from the solid-seeming walls of classical physics to the probability clouds of quantum mechanics, from the nuclear furnaces of stars to the delicate chemistry of life, from abstract equations to the concrete technologies that surround us. Let us now gather these threads together, not to tie them in a tight knot of conclusion, but to let them weave themselves into a soft blanket of understanding that can carry you gently toward rest. The question we have been contemplating, why can particles tunnel through walls they don't have energy to cross, no longer seems like a paradox demanding resolution. Instead, it has become a familiar companion, a gentle reminder of the beautiful strangeness of the universe we inhabit. We have seen how particles are not the solid spheres our intuition suggests, but waves of possibility that naturally extend into and through barriers. We have understood how the mathematics of quantum mechanics, strange as it might seem, perfectly describes and predicts this tunneling behaviour. We have witnessed the experimental evidence, overwhelming and precise, that confirms tunneling happens exactly as the equations say it should. Perhaps for tonight, the questions themselves are enough. Perhaps it is enough to know that we live in a universe where the impossible happens regularly, quietly, beautifully. where barriers that seem absolute contain within them the possibility of passage, where patience and probability can accomplish what force and energy cannot, where the laws of nature are not rigid constraints, but include a kind of quantum flexibility that makes possible phenomena that a purely classical universe could never support. As you lie there, feeling perhaps the weight of your body settling deeper into rest, your breathing becoming slower and more regular, consider that you don't need to hold on to all the details we've explored tonight. You don't need to remember every equation, every experiment, every implication. Let them drift through your awareness like clouds across a night sky, present but not demanding attention, beautiful but not requiring analysis. The universe will continue its quantum dance whether you're actively thinking about it or not. In the silence between your breaths, particles are tunneling. In the cells of your body, enzymes are using quantum tunneling to catalyze the reactions of life. In the electronic devices around you, electrons are tunneling through carefully engineered barriers to store and process information. In the rocks beneath you, radioactive nuclei are decaying through alpha particle tunneling, their half-lives determined by quantum probability. In the stars above, protons are tunneling through electromagnetic barriers to fuse and release the energy that lights the universe. All of this continues, moment by moment, whether you're aware of it or not, a constant quiet background to existence itself. The need to fully understand every aspect of quantum tunneling can soften now, making room for a simpler feeling. Awe at the elegant strangeness of nature, gratitude that we've evolved the capacity to discover these hidden truths, peace in knowing that the universe is far more interesting than we might have imagined. You don't need to solve the mysteries of quantum mechanics tonight. You don't need to reconcile all the paradoxes or understand all the implications. It is enough to rest in the knowledge that you are part of this quantum universe, made of it, sustained by it, capable of contemplating it. Think of all the barriers that seemed impermeable before quantum mechanics was discovered. The barrier that prevented us from understanding radioactive decay. The barrier that kept us from explaining how the sun shines. The barrier that limited our ability to see and manipulate individual atoms. One by one, these barriers have been crossed, not by brute force, but by understanding the quantum nature of reality, by recognizing that nature itself provides subtle passages through seemingly impossible obstacles. What barriers that seem impermeable today might yield to future understanding? What impossibilities might become possible as we learn more about the quantum foundations of reality? But these are questions for another time, for waking hours and active minds. For now, let them float away like leaves on a gentle stream. The universe will keep its secrets and reveal them in its own time. Particles will continue to tunnel whether we're watching or not. The sun will keep shining through quantum fusion in its core. Life will continue its quantum-assisted chemistry. The great cosmic dance of probability and possibility will continue, and you are part of it, even in sleep, even in the quietest moments of rest. As the words grow slower and the spaces between thoughts grow longer, like the increasing wavelength of light shifting toward the red as it climbs out of a gravitational well, feel yourself beginning to drift. Not through any barrier, for there are no barriers to sleep when the mind is ready, but into that soft space where consciousness begins to dissolve into dreams, where the sharp edges of waking thought become the fluid possibilities of sleep. This too is a kind of transition, not quantum tunneling, but something equally mysterious, the daily journey from waking to sleeping and back again. The universe itself seems to whisper that it is safe to let go, safe to stop trying to understand everything, safe to rest in mystery. The same quantum laws that allow particles to tunnel through barriers also hold your atoms together in stable configurations. The same probabilistic processes that make tunneling possible also ensure the reliable chemistry of your body. You are held by these laws, supported by them, made possible by them. They worked before you knew about them, and they'll continue working while you sleep. In your dreams tonight, perhaps you'll find yourself in quantum realms where the usual rules don't apply, where you can be in multiple places at once, like a particle in superposition, where you can pass through walls without breaking them, like a tunneling electron, where the impossible becomes possible through dream logic that might not be so different from quantum logic. Dreams and quantum mechanics share a certain quality, Both reveal that reality is stranger and more flexible than our waking classical intuition suggest. Let the mathematics fade now into the background, like equations written in sand being gently erased by waves. You don't need to carry the formulas with you into sleep. Let the experimental apparatus disappear, the scanning tunneling microscopes and particle detectors and laboratory equipment dissolving into the darkness. You don't need to maintain the precise measurements and observations. Let even the concepts themselves begin to soften. Particles and waves, barriers and probabilities, classical and quantum, all blending together into a peaceful understanding that needs no words. What remains is simply this. You live in a universe where particles can tunnel through walls they don't have energy to cross. This is not a bug but a feature, not an exception but part of the rule, not a violation of law but a consequence of deeper laws. This quantum tunneling makes possible the stars, the elements, life itself. It enables technologies that improve our lives and tools that expand our understanding. It reveals that nature is far more interesting than we might have guessed, full of surprises and possibilities, always ready to confound our expectations in the most beautiful ways, and you, resting there in the darkness, are proof that the universe's quantum strangeness is compatible with stability, with life, with consciousness. You are made of particles that obey quantum laws, including the possibility of tunneling. Your existence depends on quantum processes, from the fusion in ancient stars that created your atoms to the enzymatic reactions happening in your cells right now. You are not separate from the quantum world, but an expression of it, a way for the universe to know itself, to discover its own quantum nature. As sleep approaches, like a gentle tide rising to carry you away from the shores of waking consciousness, remember that the mysteries we've explored tonight will still be here tomorrow. Quantum tunneling will continue happening all around you and within you. The questions about what it means, about how to interpret it, about what other quantum secrets nature might hold, will remain for future contemplation. But for now, for tonight, it is enough to have touched these mysteries, to have spent time in their company, to have wondered at the beautiful strangeness of the quantum world. The universe continues its quiet work. Particles tunneling through barriers, stars shining through quantum fusion, life persisting through quantum chemistry, and you, drifting towards sleep, remain part of this vast, gentle process. The same laws that govern quantum tunneling govern the atoms of your body. The same probabilistic processes that allow the impossible to occasionally happen ensure that the possible reliably does. You're held by these laws, these processes, this elegant mathematical structure that underlies all of reality. And so we return one last time to the question that has guided us through this gentle exploration of the quantum realm. Why can particles tunnel through walls they don't have energy to cross? But now, having journeyed through the mathematics and experiments, through the cosmic and biological implications, through the philosophical and human dimensions of this phenomenon, we can hold this question differently. Not as a problem to be solved, but as a doorway to wonder, not as a paradox, but as a revelation of nature's deeper character. The answer, if we can call it that, is both simple and profound. Particles can tunnel through walls they don't have energy to cross because particles are not what our classical intuitions tell us they are. They are not tiny, solid spheres moving through space like miniature billiard balls. They are waves of possibility, quantum probability distributions that naturally extend into and through barriers. When a particle encounters a wall, its wave function doesn't stop abruptly, but penetrates into the barrier, decreasing exponentially, but never quite reaching zero. If the barrier is thin enough, some amplitude emerges on the far side, giving a non-zero probability of finding the particle there. This is not a violation of physical law, but a consequence of the true laws, the quantum laws that govern reality at its most fundamental level. Energy is still conserved, just understood in a more subtle way that includes quantum uncertainty. Probability still rules, just probability of a quantum rather than classical kind. The universe still makes sense, just a different kind of sense than our evolved intuitions would suggest. Particles tunnel through barriers because that's what particles do when they're being truly themselves. Not classical approximations, but quantum entities with wave-particle duality. As you rest there in the darkness, perhaps on the very edge of sleep now, know that the universe continues its quantum dance all around you. In the silence between atoms, in the spaces between stars, in the gaps between thoughts, Particles are exploring barriers, their wave functions spreading out, occasionally tunneling through to the other side. This is happening now, has always been happening, will continue happening long after we're gone. It's not dramatic or violent, but quiet and probabilistic. A gentle exploration of possibilities that has been going on since the universe began. In the stars scattered across the night sky, even if you cannot see them from where you rest, nuclear fusion continues its patient work. Protons that don't have enough energy to overcome their electromagnetic repulsion are nonetheless tunneling close enough to touch, to fuse, to release the energy that lights the cosmos. Every star is a vast collection of tunneling events, each one individually improbable, but collectively inevitable, given enough particles and enough time. The same process that created the calcium in your bones, the iron in your blood, the carbon in your DNA. You're made of stardust, and that dust was forged through quantum tunneling in the hearts of dying stars. Here on Earth, in the quiet darkness that surrounds you, life continues its quantum-assisted chemistry. In plants performing photosynthesis even in the dim starlight, electrons tunnel between molecules with remarkable efficiency. In bacteria in the soil, enzymes use proton tunneling to break down organic matter and recycle nutrients. In your own body, even as you drift towards sleep, countless biochemical reactions proceed with the help of quantum tunneling. Your metabolism doesn't pause for sleep. It continues its work, quieter perhaps, but never stopping, sustained by quantum processes that classical chemistry alone could never explain. The atoms that make up your body are themselves stable only because of quantum mechanics. The electrons around each nucleus exist in standing wave patterns, quantum orbitals that give atoms their size and chemical properties. These electrons are constantly exploring their quantum boundaries, their wave functions extending beyond what classical physics would allow. They don't spiral into the nucleus, as classical physics predicted they should, because quantum mechanics forbids it. They exist in stable quantum states, the same states they've occupied since these atoms were first formed billions of years ago. Think of the vast spans of time involved. The hydrogen atoms in your body, mostly in the water that makes up about 60% of you, have existed since the first few minutes after the Big Bang. For over 13 billion years, these protons and electrons have been following quantum laws, their wave functions evolving, occasionally tunneling, always obeying the strange and beautiful rules of quantum mechanics. The carbon atoms in your body, forged in stars that died before our sun was born, have been quantum mechanically stable for billions of years. You're not just old, you are ancient, made of particles that have been dancing their quantum dance since nearly the beginning of time, and this dance continues. While you sleep tonight, particles will tunnel. In the computer chips and memory devices around you, electrons will tunnel through barriers to maintain stored information or process data. In any radioactive materials nearby, perhaps in smoke detectors or old watches with radium dials, alpha particles will tunnel out of nuclei in random but statistically predictable decay events. In the cosmic rays that constantly rain down from space, particles will tunnel through atmospheric nuclei, creating cascades of secondary particles. The quantum world doesn't sleep. Yet there's something deeply peaceful about this constant quantum activity. It's not chaos, but a kind of dynamic stability. Not random, but probabilistic. Not violent, but gentle. Particles tunnel when conditions are right, following mathematical laws of extraordinary precision and beauty. The universe explores its possibilities patiently, methodically, one quantum event at a time. There's no hurry, no urgency. The sun will continue fusing hydrogen for billions of years. Your DNA will continue replicating with quantum-assisted fidelity. The electrons in computer chips will continue tunneling exactly as designed. The quantum world is remarkably reliable, despite its probabilistic nature. Perhaps this is one of the deepest lessons of quantum tunneling, that uncertainty and reliability are not opposites but can coexist beautifully. Individual tunneling events are unpredictable, but their statistical behavior is precisely determined. We cannot say when any particular radioactive atom will decay, but we can predict with extraordinary accuracy how many will decay in a given time. We cannot track individual electrons tunneling in a flash memory device, but we can engineer devices that store data reliably for years. The universe has found a way to build stable, predictable macroscopic behavior on a foundation of quantum probability. As you drift closer to sleep, feeling perhaps that boundary between waking and sleeping becoming softer, more permeable, like a barrier that consciousness can gently tunnel through, remember that questions about quantum tunneling are also questions about existence itself. Why is there something rather than nothing? Why does the universe follow mathematical laws? Why are those laws just right to allow atoms, stars, planets, and life? Quantum tunneling doesn't answer these ultimate questions, but it gives us a glimpse of how deep the mystery goes, how strange and wonderful the answers might be. The fact that we can ask these questions, that consciousness has emerged from quantum processes to contemplate quantum processes, remains one of the greatest mysteries of all. Your brain, processing these final thoughts before sleep, is performing computations that we don't fully understand, possibly using quantum effects that we're only beginning to discover. The boundary between the quantum and classical worlds runs right through your consciousness, through your ability to observe and collapse wave functions, to measure and thereby influence quantum systems. You're not just in the universe. You're a way for the universe to observe itself, to collapse its own wave functions, to turn quantum possibilities into classical realities. But these deep mysteries can rest now. You don't need to solve them tonight. You don't need to understand everything about quantum tunneling or consciousness or the nature of reality. It is enough to have touched these mysteries, to have spent time contemplating them, to have appreciated their beauty and strangeness. The universe will keep its secrets and reveal them gradually, in its own time, to those who patiently seek to understand. Your part tonight has been simply to wonder, to listen, to let these ideas wash over you like gentle waves. In the morning, when you wake, the world will seem solid and classical again. Walls will be walls, barriers will be barriers, and the quantum strangeness we've explored tonight will retreat into the microscopic realm where it usually hides. But perhaps you'll remember in some quiet moment that beneath the solid appearance of things lies a quantum reality, where particles tunnel through barriers, where possibilities are explored rather than paths followed, where the impossible happens regularly but rarely. Perhaps you'll look at the sunlight and remember that it exists because of quantum tunneling in the sun's core. Perhaps you'll feel a new appreciation for the quantum processes that sustain your life with every breath, every heartbeat, every thought. Or perhaps you'll forget the details but retain just a feeling, a sense of wonder at the universe's hidden depths, a comfort in knowing that reality is far stranger and more beautiful than it appears. That would be enough. The universe doesn't require us to understand it completely. It doesn't demand that we remember every equation or experiment. It simply continues its quantum dance, and we, made of quantum particles ourselves, dance along with it whether we're aware of it or not. The silence between stars is not empty but filled with quantum fields, virtual particles popping into existence and disappearing again, the quantum vacuum that underlies all of reality. The silence between atoms in your body is not empty but filled with electron wave functions, probability clouds that give matter its form and properties. The silence between thoughts as you drift towards sleep is not empty but filled with neural activity, perhaps including quantum processes we don't yet understand. Even silence, even emptiness, even nothingness itself is quantum mechanical, filled with possibilities, fluctuations, the potential for particles to tunnel into existence from the vacuum itself. And in this quantum fullness that underlies all of reality, you exist as a temporary but beautiful arrangement of particles, a pattern that has emerged from quantum processes to contemplate quantum processes. Your existence is both wildly improbable. What are the chances that atoms would arrange themselves into you? And yet inevitable given the laws of physics and enough time. You're a quantum fluctuation that has learned to think, a collection of tunneling particles that has developed consciousness, a wave that has collapsed into wondering about waves. As the final moments of waking consciousness fade like the last light of sunset, like a wave function gently spreading out into the darkness, remember that you remain part of this quantum universe even in sleep. Your atoms don't stop obeying quantum laws when you're unconscious. The tunneling continues, the wave functions evolve, the quantum processes that sustain your life carry on. You can let go, trusting in the same laws that have kept your atoms stable for billions of years, the same processes that will continue whether you're thinking about them or not. Somewhere in the cosmic darkness, particles are tunneling through barriers they don't have energy to cross. In distant galaxies, in nearby stars, in the earth beneath you, in the air around you, In the very atoms of your body, the impossible is happening quietly, gently, continuously. This is not a universe of rigid mechanical laws, but one of fluid quantum possibilities. Not a prison of classical determinism, but a garden of quantum probability. Not a place where barriers are absolute, but one where every wall contains within it the possibility of passage. And you, drifting now into sleep, are carried by these same quantum laws, held by them, made possible by them. You are a small but precious part of the universe's quantum story, a brief but beautiful chapter in its exploration of what matter can become when it arranges itself just so. Your consciousness, emerging from quantum processes, contemplating quantum processes, and now releasing its grip to sink into sleep, is one of the universe's ways of knowing itself, of discovering its own strange and wonderful nature. The question we began with, why can particles tunnel through walls they don't have energy to cross, has become a lullaby, a gentle reminder of the universe's quantum nature. The answer whispers through the darkness, because that's the kind of universe we live in, one where waves and particles dance together, where probability and possibility interweave, where the impossible happens regularly in the service of making possible everything we see and are. This is your universe, your reality, your quantum home. And as you finally drift away, carried into sleep by the same mysterious processes that carry particles through barriers, you remain part of this vast, gentle quantum unfolding. The universe continues its patient exploration of possibilities. Stars continue shining through quantum fusion. Life continues its quantum-assisted chemistry. And you, sleeping peacefully, are held in the embrace of quantum laws that never sleep, never stop, never cease their quiet work of making the impossible possible, one tunneling event at a time. Rest now in the knowledge that you live in a universe strange enough to allow quantum tunneling, stable enough to support your existence, and wonderful enough to have produced beings capable of discovering and marveling at its quantum nature. You are home in this quantum cosmos, safe in its mathematical embrace, part of its ongoing story, and tomorrow when you wake, the quantum dance will continue, and you'll still be part of it, whether you remember these words or not, whether you think about quantum mechanics or not, whether you believe in the impossible or not. The particles tunnel on. The universe unfolds according to its quantum laws, and you, small and temporary but precious beyond measure, sleep peacefully in the midst of this vast, beautiful quantum mystery, wrapped in the same laws you've been listening to tonight, carried by the same processes that let particles cross barriers they cannot climb, held gently by a universe that keeps tunneling, shining, and unfolding in the dark. Good night, quantum dreamer. Sleep well in your quantum universe, and may your dreams tonight be filled with the gentle impossibilities that make everything possible.